Okay. Good morning, everybody. It's listen. Okay. Thank you for being here with us today. After the cancellation of the seminar on March 23rd due to COVID restrictions and consequences at the social and economic level that the pandemic has generated worldwide, I'm very grateful to open the LIFE Methamorphosis final event with such a large amount of participants. More than 150 people have registered without taking into account the project partners and speakers. We welcome participants from Brazil, Denmark, Italy, Japan, Netherlands, Portugal, Sweden, and of course the locals. Thank you, especially the European Commission, the speakers, the advisory board, and project team for making LIFE Methamorphosis project possible. The metropolitan area of Barcelona is a supra-municipal authority that provides services related to environment, urban planning, housing, transportation, mobility, and economic development for the 36 municipalities included in the metropolitan area, more than 3 million inhabitants and an area of 600 square kilometers. The Directorate of Waste Prevention and Management Services, which I lead, is in charge of territory municipal solid waste management and treatment. We have aligned our priorities with the environmental objectives of the European Commission. Participating in the LIFE Methamorphosis project, co-financed by European Commission through the LIFE program, has allowed us to further our work and advance innovation towards these objectives. In LIFE Methamorphosis project, among other things, metropolitan area of Barcelona is responsible of the communication and dissemination actions. This final seminar, which focuses on innovation as a core theme, is the final fruit of our effort. Exactly, it has been developed over 5 years. As you will have seen in the agenda, the seminar is organized into 3 different sections. The first one, the consortium, will present the project results and achievements. In the second one, we will have the opportunity to learn about innovative projects related to the productions of biomethane. And finally, we will listen experiences and projects about innovation on waste and wastewater treatment and management. We will also have time for questions at the end of each section. The conference will be held entirely in English, given its international character and the interest for public administrations, the industrial sector, the scientific community, the media and dissemination, and citizens concerned about the sustainability and mobility of the future worldwide. Well, I don't want to take too much of your time now. José Ramón Vázquez from Aqualia, coordinator of the LIFE Methamorphosis project, will introduce himself and the project. Thank you very much.
Thank you very much, Joan Miquel, and it's a real pleasure and an honor to be here with you, and thank you very much for organizing this closing event. Of course, we would have preferred to have it presential in real life and not in virtual life, but this pandemic situation has changed somehow our plans. So please confirm that you can see now my presentation. Is it appearing?
Yes, it is, Jose.
Yes, it's okay.
Wonderful. Great. So even technology works, which is a good sign. So thank you all assistants for being here today. And it's a real honor and a pleasure to introduce you this wonderful project, the LIFE Methamorphosis project, which has been a 5-year trip with an amazing team. I must admit that as a coordinator, I was surprised day by day by the quality and the professionality of all the members of this big and challenging project. So the title is somehow complicated: Waste Streams Treatment for Obtaining Safe Reclaimed Water and Biomethane for Transport Sector to Mitigate Greenhouse Gas Emissions. It's something that you wouldn't say easily in a conversation with friends. But it highlights somehow the main aims of this project. We would like to harvest biomethane for the transport sector out of wastes. And we know it's a challenge, and you know that now the European Union is talking a lot about circularity, circular economy, and how we can do more with less, and how we need to harvest everything we can from wastes. So there you can see as well the project team. So let me please tell you a bit more about the project itself. So the project has two demo sites in Catalonia, Spain. So you probably all know Catalonia well. And the project has a total budget of a bit more of 3.5 million euros. So it's quite a big LIFE project with 60% contribution from the European Union. So we are very grateful to the European Union and EASME team and NEMO team to help us, to give us the funding and the advice in the running of the project that we are closing right now. So the project started already 5 years ago, and as I said, we are, I think, a very strong team of private entities with public entities, which is, I believe, one very interesting way of doing innovation. So putting together public and private entities, you can see that the circularity obliges somehow to put together different sectors. So we have the water sector, and we are the coordinator in Aqualia. So we are specialists in treating water. Then we have MCC Environment, which is also, we are part of the same group, the FCC group, a big holding. And FCC Environment deals with waste management, solid waste management. Then we have two more very big private partners. So Naturgy, which does everything related to energy, and SEAT, so a very important car brand in Spain. So we are 4 private entities from different sources of, or with different, I would say, products, but we need to merge together to develop new solutions to harvest this potential out of waste. Then we have AMB, which is, of course, coordinating the dissemination activities, and has been very important since they are the owners of one of the demo sites, and then the Generalitat de Catalunya through its Institute of Energy that also brought us an important view on how the energy sector moves in Catalonia and even at European level, and how our project can be replicated further, which is, of course, very important in this LIFE project calls. So what are the expected impacts within the LIFE Methamorphosis project? We would like to develop new upgrading and biogas cleaning systems to be able to produce biomethane, which can then be used in fleets of light and heavy vehicles. So you probably are aware that biogas is mainly used in Europe for heat purposes or for electricity production, but within the Metamorphosis project, we want to go a step further, and we want to provide biofuels for cars or trucks. Then we also want to reduce the energy demand of waste management. As you are probably aware, leachate treatment and liquors in organic fraction municipal solid waste plants is a big issue. It needs a lot of energy. When I remember when we started doing pronostics many years ago, when we were writing the proposal, we were guessing that the energy requirement for these leachates or liquors treatment was around 5 kilowatt-hour per cubic meter, and you will see later in this meeting that it's much higher than that. So the amount of energy you need to clean these liquors is huge, and we would like to reduce it. We also want to reduce the greenhouse gas emissions up to 80%. Of course, LIFE Methamorphosis frames into a LIFE climate change mitigation goal, so we need to tackle, and we need to do more with less, and we have to develop new products which are economically viable, but also we need to take care of environment. So everything we do should be with the appropriate environmental impact. Another important point of the project is to increase the quality of the treated water with the commitment to meet reuse quality. And then finally, we need to get cost-effective treatment plants applying innovative anaerobic processes for organic matter and nitrogen removal. And after me, my colleague Tony will explain a bit more about this. But so the main objective of the project is a dream I had when I was a child. If you remember, it was back in '85. I was only 5 years old. I saw this very nice car with Marty and Doc moving just with bio-waste. And I thought, what an interesting thing. It was already many years ago. Unfortunately, the cars nowadays still don't fly. But this is the team we built to make this dream come true. So we are here, the partners. It was back in 2015 when we launched the project, and times goes fast. It was like it was yesterday, but from this picture till now, 5 years passed, and many things happened at the demo sites. So to frame the project within the biogas sector, you probably are aware that Spain is not a big player in world's biogas sector. So you can see here, I don't know if it's big enough, but of course in Europe, the main player in biogas production is Germany. Then we have United Kingdom, that is still European Union, not for long probably, but it's still there. Then we have Italy, France, Czechia, Denmark, Netherlands, Poland, and then comes Spain. As you can see, landfill gas and sewage sludge are important vectors, and then there are many other sources of anaerobic fermentation, and each country has its own rules, his own subsidies, and so the sector is quite diverse. And probably some other speakers will come back to this point. But in our case, we don't want to talk about biogas in general. We want to talk about biomethane use in transport in Europe. And in this point, the number of players is still lower than the one I mentioned before. And Sweden and Germany are here the main actors, I would say. So I must admit that when we started the project is ambitious, want to bring new technologies and to provide new tools to harvest and use biomethane in the transport sector, but it's challenging. I mean, as you can see, the number of replications in this field is low, and that's why we needed the help from the European Union to make this dream come true. So compared to other biofuel sources such as biodiesel and bioethanol, biogas is still a small player, but we have good hope that this might change in the upcoming years. And why? Because, for example, a country like France set up a clear objective, and they want to have 100 renewable gas mix, or at least they are trying to push it forward to have a completely renewable gas mix in 2050. So it brings us hope, and it brings us also our projects might somehow help this policy change and policy implication, and how to move from our actual linear system into a circular economy context. But what is the potential? I was telling you about harvesting biomethane from waste. How is the waste sector doing? The truth is that in Spain, we are doing quite bad. You can see here the figures on where it is compared, the theoretical potential currently collected as bio-waste separated from the normal waste. So how much bio-waste is collected separately? And you can see that Spain hasn't done his homework. We are still at a very low level of separate collection. So you know that you probably are aware that the new directive, European directive, made obligatory to collect separately bio-waste by the end of 2023. So we have a lot of homework to do in Spain about this topic. But I must also admit that Catalonia is a good player in that game, and it was highlighted as a success story because Catalonia has implemented already some years ago strategies to harvest separately bio-waste, collect it, and valorize it. So there is room for producing biomethane. There is a lot of bio-waste which is still not separately collected, and that might end up fueling our cars. Finally, just a quick appointment about the liquors treatment in the municipal solid waste plants and also in the agro waste plants. It's a nightmare. It's normally the leachate and the liquors treatment is quite heavy in consumption of resources, in energy, in chemicals, and so on. Why? Because this treatment is normally based in aerobic processes. The old activated sludge process was invented more than 100 years ago, so I think it's time to get rid of it. It's true that lately the aerobic membrane bioreactor arose, and many of the liquors treatment plants are based on this technology, which is an evolution of the old activated sludge plant. But it's still an aerobic process that needs energy to get rid of organic matter. So, as an example, in Aqualia, we know that the potential energy content of urban wastewater is typically 2 kilowatt-hours per cubic meter. So we are not proud to say that in Aqualia we are spending 30 million euro a year to treat our wastewaters, when we should be harvesting energy out of it. And as you can imagine, urban wastewater has only 0.5 grams per liter of CO2. And then Tony will tell you that the amount you can find in these liquors is several times bigger than that. So we are just wasting money putting air into these liquors, okay? So that's just my very quick introduction. This is the 2 demo sites that now my colleagues from the project will tell you about. The one in Barcelona, in the municipal solid waste management facility, Ecopark 2, and then the demo site in Lleida in an agro-food plant in Porcaporc's farm. Okay, so I don't want to take much more time with the introduction of the project. I hope you will enjoy the session, and I will be helping you through the different presentations. So I will tell the speakers when you have only 1 minute more. Remember that for this first session, we will have 4 speakers. Each one will have 12 minutes. I will tell you when you have only 1 minute left. And please, we will keep the questions to the end of the session. We will have 10 minutes for questions. So after our speaker finish their presentation, please raise your hand. You will see a button where you can raise your hand. I will be giving you the voice to ask your question. Please introduce yourself and tell you your question at the end of the session. So now I thank you all for being here, and please, Tony, continue and tell us about the umbrella prototype, please.
Okay, Jose, it's my pleasure.
Remember that you have 12 minutes. I will be counting it.
Okay. Please, can you tell me if you can see my screen?
It's still now, yes.
Yes, yes.
Yes? Okay. Thank you very much for the introduction, Jose. It's my pleasure to present the results of the Umbrella project and prototype experience. Jose has already made it clear that one of the main roles of Aqualia was to be the coordinator consortium in Metamorphosis. And there are two keywords of the project. I would say one of them is biomethane, and the other one was, if you remember the term stream, the wastewater. As Aqualia, as a water utility, I'm going to speak about this more about, we'll stress more about this term, about the stream and the water treatment. Aqualia has had the main role of one of the sub-projects, which is the prototype we have named Umbrella. And we were the main executor of the plant, being in charge of the design, the construction, the commissioning, the operation, and the demonstration prototype. Okay. So let me first of all speak a little bit about the context, about the background. Umbrella is a project that takes place in the urban waste industry. And as you know, in Europe, we are gradually leaving the landfilling system and moving towards mechanical biological treatment systems for our solid organic waste. This slide represents the treatment, including some large and approximate numbers of the EcoPark 2 installation of Barcelona, where the Umbrella prototype has been located all this time. And as you can see, as you can see in the right side, once all the organic matter has been processed, 3 fractions are obtained. On the one hand, we all know that we obtain biogas with a high calorific value, from which we can extract bioenergy. We also know that there's a stabilized digestate that we obtain a certain agronomic value and is therefore usable as soil amendment or even as a fertilizer. However, there's a 3rd fraction, which is the stream, which is the liquid fraction. And to this day, it continues to be usually considered as a waste of all this entire industrial process. And its potential, it's still not used. So Aqualia wants to change this approach through Umbrella. Jose told already about that. Just, you know, the current way of how this liquid stream is treated is just putting air. Usually there's technology called aerobic membrane bioreactor, putting air to oxidize nitrogen and organic matter. These systems are mature. They are, to admit, they are effective, but they are still areas to improve the efficiency. They present high aeration needs for the oxidation of all compounds. Furthermore, it's based on aerobic process. That means that we produce a large amount of excess sludge. And finally, well, there can be or there can happen eventual undesirable heating or foaming during the operation. So with Umbrella, what we want is to overcome all these limitations. First, we consider that the liquid can still be anaerobically treated. We can still squeeze more methane and simultaneously remove organic matter. After the membranes, you can see the liquid that we obtain is it has almost no turbidity, but we still have to remove the nitrogen. We do this with Elan system, which this is own technology from Aqualia, and this stands for in Spanish for autotrophic nitrogen removal. And finally, we generate a biogas stream that will be treated with a conventional upgrading process. And the Aqualia's also own technology called Abad Bioenergy and obtain biomethane for automotive use. If you are not familiar with the wastewater sector, sometimes to understand this process may sound complex and technical terms are not always easy. So I suggest you to take this funny slide to think. This may help to better understand what we are trying to do with Umbrella. Imagine a cow with several stomachs. The first stomach is the anaerobic digester that already exists. What we suggest is that after this anaerobic digester, we still have a second stomach, which is this NMBR, this anaerobic membrane bioreactor. We produce biogas like a cow, and we have also coupled ultrafiltration membranes. You can imagine they are kind of kidneys that produce a liquid with a high concentration of nitrogen, like urine, and without solids, low turbidity and high ammonia content, as I said. Okay, this is maybe just to understand a little bit much better what we are trying to do. And now let me go through the results because the time is very limited. The first thing we have verified is that the liquid is still treatable. Process, we can still produce biogas, that we can remove a large amount of organic matter. Well, the exact number of this potential were calculated thanks to collaboration with the University of Santiago de Compostela and other previous projects like Smart Gas. Demonstrated that it is possible to remove pollutants in the time, and being above the performance objectives that we had set. This is a very good news because this confirms the first step of the technical viability of the Umbrella project. And furthermore, another thing, in a biogas with a very high methane content, which means this is with a very good quality. Although the good results, the performance can be improved, especially if we tackle the ammonia inhibition, which was present during all the time. So the ammonia inhibition on the anaerobic process. Right now, we are compiling all these results and write a paper about this question with Professor Flotats, which is also going to speak today, with the area metropolitana of Barcelona. The ammonia inhibition can be partially solved if we increase the sludge retention time. I don't want to get much deep about that, but sludge retention time is just the contact time between microorganisms and the wastewater. Another previous R&D project called Smart Gas, where Aqualia was participating, we could conclude that the ammonia content could be also partially removed with a stripping process in a very efficient way. All these lessons inspired a new LIFE project that is called Infusion, and that already started in this month of September. Aqualia is also participating, Area Metropolitana of Barcelona is also participating. Ecopart del Besós it's also participating in that new project. So when we deal with biomembrane bioreactors, the success of the filtration process is essential for the global success. So we need to filter in a very good way. And the fouling must be controlled at all time. So in a collaboration with the University of Delft in the Netherlands, it was demonstrated that the sludge of the NMBR has a very poor filterability, which means that it's difficult to be filtered through the ultrafiltration membranes. But we could also demonstrate that some compounds remain on the membrane even after chemical cleanings. This forms a layer that decreases the performance. This is called irreversible fouling. Fortunately, we have also good news. We could manage the filtration process by means of alternating cross-flow velocities. We found the key. And this was absolutely essential for a sustainable ultrafiltration. We consider that it is better to decrease the cross-flow velocity or apply backwash cycles. We finally will also have stayed and suffered clogging and strubite events, and they must be just under control and taken in account in the maintenance of this system. So regarding the ELAN process, the removing of the nitrogen, we observed that the first necessary process, which is called the nitritation, showed to be very active. This was a success under any condition. So this is not a limiting process. By the other side, the nitratation, which is undesirable, we don't want to have this process, was also always under control. Always when we add this ratio, this proportion between soluble chemical oxygen demand and nitrogen. This was a very good news because that means that we can that nitrate was always below the discharge requirements. And another very interesting conclusion that has arrived by the University of Santiago de Compostela, which were one of our scientific assessors in Metamorphosis, was that if we want to promote the anamox activity, it is essential to have a low proportion between this organic matter, soluble organic matter, and nitrogen. So this means that the performance.
1 minute, Tony.
Thank you, thank you. The performance of the NMBR must be really as good as possible. So let me speak about the upgrading. We have two types of conclusions. From the one side, we can distinguish the conclusions regarding the biomethane stream. The quality requirements for biomethane obtained for vehicular use were always met. We achieved to produce about 1,500 cubic meters. We have faced several electromechanical incidences with the upgrading plant. And this led us to conclude that the upgrading membrane-based technology is not mature for small sizes and for small users. So we need really more reliability, specifically for small sizes, not for big sizes. So regarding the treatment of the off-gas, which is the gas stream generated during the upgrading process, and this off-gas is very poor. It has less than 40% of methane, but we were glad to see that with the Aqualius technology about bioenergy, we could transform this off-gas into useful biogas, removing all the CO2 as we can, and closing the loop for the upgrading and reclaiming biogas. And that will be all from my side. Thank you for your attention. I hope it was interesting for you, and I will be glad to answer your questions. Thank you very much.
Thank you very much, Tony. Of course, you demonstrated how many hot topics are being handled in Umbrella Prototype, and we are happy and thank you so much for your efforts there in the when coordinating and leading the activity there. So now let's move to demo site 2, and please, Carmen from Naturgy tells us how you achieved the extraction of energy out of the farm waste, please.
Okay, thank you, Jose. I want to share. You see the presentation, don't you?
Yes, perfectly.
Okay, good morning. Thank you all for attending this event, and thank you for the European Union for helping us to participate in this kind of project. I'm going to present the project that we developed in Naturgy as part of the Metamorphosis project. Our part is called Metagro. Metagro prototype is an example of how you can use the energy from wasted and use it in transport. In this case, the wasted were from a farm, specifically from an animal wasted. The project was implemented in Vilassana, a small village in Lleida, Catalonia. The biogas was produced from 3 anaerobic digesters that are already existing in the farm. This is the farm site, and this is the place where the upgrading is located. Just beside the upgrading container, the gas station is. The biogas produced from the anaerobic digestion comes from 3 different types of wastes. 45% are from pig slurry, 50% from sewage slurry from a wastewater treatment plant, and the rest, the 5% wasted from the food industry located near the farm. The farm uses around 45 tons per day of wastage to produce over 170 cubic meters per hour. The biogas produced in the anaerobic digesters is sent to the upgrading plant, where the biogas is treated to produce biomethane with high quality, enough to be used in vehicles and even for injecting into the natural gas grid. It complies with the Spanish legislation for injecting into the grid. Biogas from the digesters has around 60% of methane, 40% in CO2, and other contaminants like sulfuric and siloxane. Besides, the biogas is saturated in water. These contaminants, as well as the water, are eliminated in the first stage of the upgrading plant by means of a pretreatment plant. The pretreatment consists in a cooling stage followed by a filtering stage. In this project, the upgrading technology selected was membrane technology, due to the fact of the size of the plant and the quality of the biogas. For this size, membrane technology is one of the most competitive and useful technology. It does not require high qualified operators, and the operating expenses are not too high. There are several technologies for upgrading that can be selected depending on biogas origin and the size of the plant. The produced biomethane will have more than 95% in methane and less than 2% in CO2. With this quality, this biomethane is equivalent to natural gas from the distribution grid, and therefore can be used for any of the natural gas uses. The project included not only the operation of the plant, but also the design stage and the construction. We evaluated the synergies and integration of the upgrading plant with the biogas plant and produced the biomethane to be used and checked in SEAT vehicles. Membrane technology is based on the design of the own membranes. Membranes are made of a specific polymer that is selective to certain gases. For example, methane is rejected while CO2 passes through the membrane. By this way, these gases can be separated. Oxygen and nitrogen are rejected, just a little part of them. Therefore, this technology must be avoided for biogas with high concentration of both gases. The membranes in this project are configured in 3 stages in order to get the higher membrane recovery. With 3 stages, the recovery reaches values around 99%, over 99%, while with 2 stages, the recovery is around 95%. During the design stage, we review and approve the basic required data, as the civil work drawing, as this one, and the general layout. The pretreatment skids were located out of the container as close as possible to the upgrading. The upgrading was also located near the farm entrance to make easy the access to the filling station. We reviewed the safety and ATEX requirements of the project, establishing the required distance among the different facilities. This is the ATEX drawing. This is a very important part of the project that has to be clearly studied from the beginning of the project. Equipment located in ATEX zone must be manufactured with specific characteristics. Also, the communication and the control system was carefully designed and reviewed in order to make the plant as automatic as possible. This plant can be controlled and monitored in remote from Madrid. This is the control network drawing where all the communication units are represented. The construction phase was less than 4 weeks. 3 weeks for civil works and connections with the biogas plant, mechanical and electrical connection, and 1 week for the installation. The equipment came from Holland pre-installed in a container and in 2 pretreatment skids. 3 trucks arrived at the farm, and the same day the main equipment were located in their place. All the project from the beginning of the design to the start of the operation was about 12 months. Here you can see the panoramic of the plant. From the left to the right, it can be seen the chiller for cooling the biogas, the blower, and the 3 filters for the contaminants, and behind the main container. Inside the container, there are the 3 stages of the membranes. Stage 1 with 5 membranes in the middle, stage 2 with 8 membranes in the lower part, and stage 3 with 6 membranes in the upper zone. As it can be seen, there is free space for increasing the number of membranes in case the biogas will have worse quality than expected, or if we would like to increase slightly the biomethane production. This is the compressor that compresses the biogas to the required pressure between 8 to 16 bar. The compressor is a screw compressor made in Italy by Adicom. It includes also filters and cooling devices for its protection. In order to monitor the biogas and the biomethane quality, the plant includes 2 multi-analyzers that informs about the methane concentration, CO2, oxygen, and sulfhydric. These analyzers take samples from different points of the process in order to make the system working in an automatic mode, adapting the frequency of the compressor to get the required quality in the biomethane. The lower the methane concentration in the biogas, the higher the required compressor discharge pressure. The gas refueling station is also part of the project. It includes a compressor and a storage to fill 2 cars. It consists of a compressor for 18 cubic meters per hour with a discharge pressure of 250 bar, with 14 pressure bottles with a capacity of 80 liters each one. The upgrading plan is monitored continuously by means of a PLC system. This is the screen from the PLC. In the control screen, it can be seen the main process starting from the digester on the left, followed by the heat exchanger for cooling the biogas, and after it's compressed with a blower. After the blower, there are the 3 carbon filters. The biogas clean of contaminants and with lower water content is fed to the compressor. The compressed biogas is sent to the membranes. Finally, the biomethane coming from the membranes with over 95% in methane is sent to the refueling station. In case the biomethane would not comply with the required quality, it will go back to the digesters. These are the big numbers of this project. The plant treated a medium flow of biogas, about 150 cubic meters per hour, and produced around 100 cubic meters per hour of biomethane. It treated more than 15,000 tons of wastage, and the electrical consumption ratio was around 0.4 kilowatts hour per cubic meter of biogas. The plant produced an energy of nearly 2,500 megawatts hour and consumed less than 140 megawatts hour in the electrical consumption. These are the cubic meters of biogas entering into the upgrading each month and the biomethane getting from the plant. The flow that can be seen depends more on the vehicle's consumption than on the capacity of the plant. The months with higher production means the vehicles were doing more kilometers than other months. Here, it reflects the electrical consumption and the electrical ratio month by month. The medium value, as I told you before, is 0.4. In this graph, it can be seen the energy produced month by month and the electrical consumption. In conclusion, in this project, the mitigated emissions of CO2 during the project was around 3,400 tons of CO2. And besides, the mitigated emissions due to the use of the biomethane in SEAT vehicles was around 93 tons of CO2 compared with using gasoline in the same vehicles. The biomethane produced in this plant was enough to fuel 148 vehicles traveling 25,000 kilometers per year, with the consequent reduction in NO2, particles, and CO2. The reduction of the greenhouse emissions and the reduction of the risk of aquifers contamination in this area was 2 of the main goals obtained from this project. Those demonstrate the transformation for farm wastage to energy is possible and very interesting. At this stage of the project, the produced energy has been used directly to transport, but our future objective would be to inject this biomethane into the distribution grid. With this solution, the production and the consumption of the biomethane will be modulated and maximized. Therefore, this renewable gas will be used not only for transport, but also for any of the possible uses of the natural gas. Thank you very much, and I hope you enjoy it. I was shorter than expected.
No, perfect. You did just perfect. That's why I saw you were already with the conclusion, so I hadn't to tell you that you had 1 minute left. So wonderful. Thank you very much, Carmen. And you clearly demonstrated how deep you went into this new story and how biomethane can be harvested from farmland. Okay, thank you very much. Let's move now to the core sector. And please, Eva Rodriguez from SEAT, tell us how it went with the running of the cars fueled with this wonderful biomethane.
Hello, I go to share the excuse me. I can not share. Excuse me. Okay, I think yeah, now. Can you see?
Perfect. Yeah, perfectly,
okay.
Eva.
Okay, excuse me. Good morning, my name is Eva Rodriguez Torres, and I have been working in the Technical Center of SEAT for 23 years. I have studied mechanical industrial engineering, and I am responsible for the durability of the mechanic of petrol and compressed natural gas engines. First of all, I would like to thank you for your interest and presence in this event. Without further ado, I will now present my paper, Results and Analysis of Road Tests with Biomethane. I hope you will enjoy it. First of all, I would like to show you the scope of the project. The starting point was to test 4 vehicles with biomethane from 2 different sources, one from Pixlure called Metagro and the other from granite waste called Umbrella. The mileage to be reached was 30,000 kilometers in each of the 4 vehicles. In total, 120,000 kilometers. Within the Metagro project are 2 vehicles, one with 1.4 liter and 81 kilowatt engine and manual gearbox, and a second vehicle with a 1.5 liter and 96 kilowatts engine manual gearbox. Within the Umbrella project, there are two vehicles, a Leon with a 1.5 liter and 96 kilowatts engine and manual gearbox, and an Arona with a 1.0 liter and 66 kilowatts engine and manual gearbox. The type of test is customer type. This is the driving that any of us could do. Road, city, highway. The driving profile is 50% motorway driving, 20% urban driving, and 30% extra urban driving. The objective is verify the resistance of compressed natural gas engine when working exclusively on biomethane. Okay, now we are going to see what effect certain components of biomethane have on engine parts. First of all, I will talk about the composition of biogas without any previous treatment. Thus, biogas is mainly composed of methane from 50 to 65% approximately, carbon dioxide 30%, oxygen is around 9–10%, nitrogen 2%, and 0.15% are other components, such as sulfur compounds, halides, siloxanes, and ammonia. It is precisely these later components that have the greatest influence on engine health. When these components are burned in the engine's combustion chamber, a chemical reaction takes place, resulting in products that are harmful to the engine. When the siloxanes are burned, silicon oxide is obtained, and this accumulates inside the combustion chamber, creating white deposit, as can be seen in the photograph on the surface of the piston, as well on the valve, spark plugs, lambda sensors, and catalyst. This deposition can produce an increase in compression, which can seriously damage the engine. And on the other hand, silicon oxide reaches the engine oil where it remains undissolved and therefore produces wear between the parts in contact with the engine. When sulfur compounds and halides are burned, sulfuric acid is produced, which is highly corrosive and attacks the engine parts, as well as the oil, since the oil has a limit on acid absorption and therefore will degrade very quickly. The evaluation of results up to 1,000 kilometers. At the beginning, when I present the scope of the project, I talk about 4 vehicles. Now I will only talk about 3 vehicles, since the Arona only reached 3,000 kilometers. This is due to the lack of gas production in the umbrella prototype plant. In order to check the state of the engines, we carry out several tests every 15,000 kilometers of tests. The tests carried out were emission test, which was positive for all vehicles, torque and engine power test carried on a roller bench, which was also correct. Compression tests were all in order, and oil analysis showed correct results. In order to see the state of the engine combustion chamber, we have used a video endoscope, which, thanks to a small camera in its end, is inserted into the hole in the spark plug and allows us to observe the inside of the engine without the need to dismantle it. The endoscope allows us to rotate 360 degrees the camera, which allows us to see the entire combustion chamber, pistons and valves. In the photograph, you can see the surface of the pistons and valve, and also the spark plugs, in which we also check the distance between electrodes. The combustion chamber and spark plugs are in good condition. The engine is in good condition after 15,000 kilometers. We can conclude that the engines after 15,000 kilometers running with biomethane shows a good state of health. We reach the total planet mileage of 120,000 kilometers, but we did not reach the 30,000 kilometer planet for each vehicle, and we had to adapt the mileage of each vehicle to the gas production in each plant. The tests have been completed, and we are currently performing the analysis and dismantling of the vehicles. I hope you found it interesting and enjoyed the presentation. Thank you very much.
Thank you very much, Eva. So we went through the 4 different presentations from the biggest players in our LIFE Methamorphosis project. And now we are happy to see that we have more than almost 100 assistants to the webinar, which I believe is amazing. So please feel free to raise your hands and raise the questions that you probably have a lot, because we have almost, we have some minutes to deal with it, and our speakers will be happy to answer all your concerns, questions, and probably challenges. So if you see there is a hand, and you can raise your hand, and I will be checking who is raising his hand, and I'll give you the chance to ask your question to our speakers. Please introduce yourself, ask your question, and tell if it's addressed to some of our speakers or if it's just a general question that any of them can answer.
Jose Ramon, sorry for interrupting you. I'm Julia from Metropolitan Area of Barcelona.
Hello, Julia.
Still, Laia Sarqueia have
to
sorry. Her presentation.
sorry. I was going too fast. I'm sorry, Laia. I completely forgot that you were.
No problem.
Okay, so my apologies. Now it's the turn to Laia Sarqueia to tell us a bit more about the biomethane potential. Laia works for the Catalan Energy Institute. So please, Laia, the 12 minutes are well deserved, and I'm sorry that I was going too fast in my mind.
Okay. Thank you, Jose Ramon. Good morning, everyone. The Catalan Energy Institute, ICAEN, is a public entity of the government of Catalonia. For us, it has been a privilege to participate in the consortium of the project with great expert companies on energy, water and waste treatment and mobility. I'm going to talk about the energy context and the potential of biomethane in Catalonia and Spain. For more than a decade in Spain and Catalonia, we have been talking about the development of biogas. It's not now a new topic. What's new is the approach we are giving to it. Upgrading from biogas to biomethane has begun to be an alternative for the direct use of this gas. Biomethane can be used for transport directly in vehicles with natural gas engines, or it can be injected into the natural gas grid to be used wherever there is a demand. A combination of factors, including the improvement of biogas upgrading technology, poor economics of electricity biogas plants, and the new opportunities for the use in transport sector, has resulted in a shift from electricity and heat production to be upgrading the biogas. The new directive for renewable energy for the next decade includes a binding target of 32% for renewable energies by 2030. It also sets a specific target of 14% for renewable energy in the transport sector, which includes a secondary target of 3.5% for advanced biofuels and biogas. The potential of biogas contribution to renewable energy generation from several ways is significant, both in terms of energy supply and reduction of greenhouse gas emission. Biogas upgrading and biomethane production offer new opportunities for the use of biogas and for the substitution of fossil fuels in transport sector. In 2017, in line with European objectives, the government of Catalonia developed, together with entities and business associations, the National Agreement for Energy Transition. Also in 2017, it was approved the Climate Change Law, and in 2018, we declared a climate emergency. The vision is to make Catalonia a decarbonized country with a renewable, clean, democratic, inclusive, distributed generation, and consumer-focused energy model. The Plan on Energy and Climate achieved the following results in 2013. Pursuing the final objective of climate neutrality in 2050, with a reduction of at least 90% of our total gross greenhouse gas emissions in total coherence with the objectives of the European Union. In addition, we have to get a 100% renewable electricity system. The goals are ambitious, and there is a long way to go. Currently, renewable energy in final consumption meet 8% in Catalonia and 15% in Spain. In terms of electricity, in 2018, renewable technologies covered 20% of demand in Catalonia and 39% in Spain. Extrapolating the experience of results of the prototypes shows the way and the possibilities for using biomethane in vehicles. However, first, it's necessary to contextualize the potential in biomethane production to know its performance in the future. In order to carry out the study on the impact of biomethane implementation, the basic information for Catalonia has been obtained from the studies carried out by ICANN for developing of energy plans. Studies carried out by IDAE on the potential for biogas generation at the state level and by academic experts from the biogas sector have also been checked. Finally, the energy potential of biogas generation is 70,000 tons of oil in Catalonia and 2,300 in Spain. Currently, the production is 55 and 231. From the accessible potential for biogas production, we have assumed an efficiency of the upgrading process, and we have measured the potential for biomethane generation. As a relevant result, we have obtained the percentage that biomethane can represent in the current total consumption of natural gas. It's between 8 and 15%. Therefore, there is the coverage we could get with the current gas consumption. Assuming a standard mobility, these are the numbers of light vehicles we could supply with biomethane. As you can see, there are many more vehicles currently consuming natural gas, although the demand for alternative fuels is expected to increase. The use of biomethane involves very low greenhouse gas emissions if compared to food-based crops, biofuels, or advanced biofuels. Biomethane could even result in negative greenhouse gas emissions when it's produced from feedstock which otherwise could emit methane during decomposition, such as manure. Several studies have been checked that link the input materials in the plants with the different uses of biogas, the production of electricity, or the upgrading and injection into the natural gas grid. Thus, we can conclude that in the case of the manure treatment and the biogas upgrading carried out at the Vilassana plant, the greenhouse gas emission savings compared to fossil energy is around 65%. For the treatment of organic waste from the eco park, we can refer the greenhouse gas emission savings up to 45%. According to the European Biogas Association studies, the use of biomethane from agricultural and livestock will save almost 200% of CO2 emissions compared to fossil fuels, and biomethane from organic waste will save 84%. Analyzing the barriers and opportunities, we have highlighted the main strengths and weaknesses for the development of biomethane in Spain and Catalonia. As weak points, we can name the operating cost and the influence of the composition of the raw material in obtaining biomethane. Around the process, there is a framework with still insufficient incentives and non-existent certificates of origin. Going to the strengths, it should be noted that this gas shows a great chance to work toward a circular economy, and it's especially relevant for local and decentralized energy production. Light road and national transport will probably be basically electric. Long distance heavy transport requires fuels with a high energy density, which means that the direct use of electricity from batteries is less suitable. That is where renewable gases play their main role. Bioenergy production as a part of bio-based economy has the potential to contribute significantly to the development of a green and low carbon economy. Thank you so much for your attention.
Thank you very much, Laia, and apologize again for going too fast in my mind.
No problem.
So wonderful. I believe it's very important to know the potential of the solutions we have developed, and you made a very good wrap up of the potential of the solution. So now I already explained how the questions work. So again, please, the audience, don't be shy and raise your hands, and we will go one by one asking your questions. So I see there is already one hand raised. So please, Maria del Mar Mico from Acciona, tell us what is your question and to who it is addressed, please.
Hi, oops. Hi, everyone. I just want to ask the SEAT representative, which was the challenge of using this kind of biogas in your motors, in your engines? Is there any difference with this biogas, and which is the main difference between this biogas and natural gas coming from oil, for example? Which was the main challenge?
The main challenge is to have another energy and to make more green, you know, the energy in our cars. And yes, we want to improve to this kind of energy, and so is the biggest objective.
Thank you very much.
But probably Maria del Mar was more curious about what kind of contaminants you expect, which might be different from the natural gas from fossil fuel, no? What were you, or exactly, what is the exact compounds that you were afraid of? So we realized that probably H2S is one of them.
I have said that the main compounds that can damage the engine is the siloxanes and the sulfurs and halides. No? The siloxane with the combustion become an oxide of silicium and can deposit over the surface of pistons, and can to hide the compression of the motor, no? And can damage seriously the engine. These compounds are the compounds that can
But so do you mean that siloxanes are more present or are more susceptible to be generated in the case of this with biogas than in the case of conventional natural gas, for instance?
Yes.
I see.
The siloxanes appear in the products for beauty, shampoos, and this thing, no, this thing for hair, for
the silicones, right?
Yes, yes, and this kind of compound are in water.
I see.
And can appear in the biogas.
I see.
That is the difference between this kind of biomethane from the grid, no? Gas
Thank you very much. Yeah. Thank you very much.
Thank you both. Okay, now we have another question from Carlos Ramos from Eurecat. So please, Carlos, ask your question.
Well, hello, good morning. Thank you very much for the presentation. I think the approach that you are searching, or do you want to develop, is very innovative, and I think is very good for the field. Well, I have two questions. The first one is about how was the approach to remove nitrogen from the wastewaters? If you can explain a little bit, and how do you see, how was the performance of the reactor? And another question is about how do you see the implementation of the full concept that you developed along the LIFE project?
Okay, so I guess the first one goes to Tony, and the second one goes to all of the speakers, probably. So, Tony, can you explain a bit more on the nitrogen removal in umbrella prototype, please?
Yes, of course. The ELAN system, which is again the acronym from autotrophic nitrogen removal, is a system based on Anamox activity, which is a very, very specific bacteria community, which was discovered about 20 years ago, 25 years ago. And Aqualia has one of these patented technology in collaboration with the University of Santiago de Compostela. And with this, with Umbrella, we try to taste this technology with this kind of wastewater. What we do in the autotrophic, we have two process. I don't want to go deeply in the biochemistry, but first of all, the Anamox, what they do is to consume ammonia, which is the normal compound of the nitrogen in the wastewater, and nitrate. So we need, which is usually not present in the wastewater. So we need to first have a first step, which is called nitritation, where we need to produce these nitrates. Once we have the proportion and nitrate, then the Anamox go inside. This has several advantages that I could not explain, but they are on the slides that I was presenting before, which are mainly less needs, about, if I'm not wrong, about 40 or 50% less, and air, that means, or oxygen, that means 40 to 50% less that we need. And secondly, Anamox are very, very slow organisms. That means that we almost don't produce sludge, which has to be managed, which is a cost usually for water utilities. Finally, we don't need external organic matter, which usually is needed for denitrification, which is the conventional nitrogen removal system that we get. This is also a very good news. I guess more or less answered your question.
Perfect.
Yes. Sorry. Do you have a removal rate or some technical details that you can?
Yes, but if we speak about wastewater, about municipal wastewater, I think, well, also Jose Vázquez is PhD on this issue. So he's really in fact, he's one of the inventors of this technology. So he probably can answer or complement my answer. But I would say that we have a top reference that could be on the municipal wastewater treatment. And this will be the nitrogen removal rate is about more or less 0.6 kilos of nitrogen per each cubic meter and day. Will be more or less the nitrogen removal rate on municipal wastewater. This is the top reference. This is wastewater. But if we go to this kind of industry wastewater, we are less than 0.1, 0.2, not more than that. This is still to be developed, to be speed up, to see what are the where we can improve this ratio. This means that it works, but it still has to be speed up or to improve or to optimize, if you want, the performance.
Yes, if I can add, exactly. So the main result we have seen with this project is that the so high ammonia and organic matter that comes out of the anaerobic MBR, most of the organic matter, of course, is not biodegradable, but it has an impact on the nitrogen removal in the LN process. And so we have seen lower rates than the rates we normally get in when treating anaerobic digester supernatrants in municipal urban wastewater plants. But it's still performing, and so the main issue is that for the final design, we will need bigger reactors compared to our conventional design in municipal urban wastewater treatment plants. That's what we got from the project. Okay, and then Carmen, please, can you tell us, according to the second question of Carlos, how far are we of implementing this kind of biomethane production technologies to the market? Because I think you made a very good exercise, and you clearly state the costs, the energetic costs of producing this biomethane. So how do you see it when you compare it with fossil fuel natural gas? How can we help this biomethane production from bio-waste to jump into the market? I know, for example, that in France there are subsidies, in Germany there are subsidies as well. What would we need to make this dream come true and to have many replications all over Europe or Spain, in this case, with this kind of technologies?
I think the main issue now in Spain, at least not in Europe, but because we are in a different point, the main issue is to get the guarantees of origin. If the CNMC published the new legislation for that, I think this will help a lot to push the market and to help people to decide to make this kind of investment. I think most of the business or farms or whatever who has biogas already, they are studying the possibility to produce biomethane, to inject to the grid, or to use for their own cars or vehicles. I think this is the main issue to the legislation to help us to push this market to be developed in the future. In the future, okay. Not. I hope next year. That is the objective for the CNMC.
So we might foresee somehow a growth in this kind of solutions in the market for the upcoming years when there is this guarantee of bio origin of the fuel we are using.
Yes, because the biomethane could be sold in a higher price than now the natural gas, so this will be the difference in the cost in operation, so the investments will be much more profitable.
Wonderful, thank you. And Laia, how do you see it in Catalonia? Do you foresee a big bet on biomethane in Catalonia, or do you believe that other renewable energies will make it quicker than biomethane?
Okay, biomethane is a slow renewable energy, but it's sure it's in development, and I think, like Carmen, it's very important guarantees of origin and some subsidies. Yesterday, we together with the IDAE, we opened a line of subsidies about this kind of plants, biomethane plants. It will be a little bit help to improve these projects. I expect in Catalonia we will work hard to develop the biomethane. So
there is future here.
Yeah, there is future. Yeah, like the film, but nowadays.
Okay, wonderful. So we reached our time. I don't know if any of the speakers want to highlight something before we do a short break for the poster presentation and to grab a coffee. Okay, so thank you, the four speakers. You did an amazing job on time, and we are proud of you and very happy to have worked close with you together in the last 5 years, and probably we still have much more projects to do together in a near future. So thank you all, and please take your coffee, and Julia from AMB will be passing the posters, so have a look at them, because they have also very interesting information, and we will be back in 15 minutes. Thank you all.
Thank you very much.
Thank you.
Thank you.
Yo no siento nada.
So hello again. I hope you all had time to rest a bit, take your coffee. And now we are moving to the section 2, where we will see presentations about different innovation projects, all of them within the topic biomethane. So we will have a panel of senior experts in the biomethane sector. And we will start with Francesco Ometo from Scandinavian Biogas, and he will tell us about also another LIFE project called EFI Sludge. So please, Francesco, the floor is yours, and we are happy to hear what are the main outputs of your LIFE project.
Good morning, everyone. Thanks for the invitation and congratulations on completing your project. Do you see my slide?
We see it, but we see it with a smaller size. I don't know if you can share the whole presentation mode, because now we see your slide and the next slide.
Let's see. I will try like this then, perhaps. If I do this, maybe I can remove this one. No, then we do.
No, don't worry. We see it.
I think it's like that. Okay, so yes, the EFI Sludge project. That's another LIFE-funded project, which started in 2015 and is actually still ongoing, and it will most probably carry on during 2021. We had some delay, and now with the project implementation site located in Norway, while we are in Sweden, we have some challenging of be able to be there at site. Unfortunately, that's impacting us quite a lot right now. But the project is still partially ongoing, and I will give you an update or as well some expectation what the project will deliver at the end. A couple of keywords of the project is the project is related to carbon emission reduction. That's the main target, focusing on industrial symbiosis and industrial wastewater treatment. So we will talk again about activated sludge system and challenging on that type of solution, but more from an industrial perspective. And that could be quite different compared to a municipal wastewater treatment. The target industry of the project is the pulp and paper industry, which has quite a high ambition and target in terms of carbon emission reduction. The current target is to reduce by 80% compared to what was emitted in 1990, so to reach from 60 million tons CO2 annual emission to 12 million tons in 2050. And overall, that type of industry has been really decreasing their carbon footprint significantly and working in both direct and indirect emission. And of course, there are different ways to tackle this aspect. One of these is related to reuse of sustainable energy and also impact on reduced emission when it comes to wastewater treatment. When we think about industrial symbiosis, we like to look at it as a mutual profitable transactions or a value adder for no product output. What is a waste for an industry could become the starting point from another industry. It's linked to eco-innovation, it's linked to improved businesses, and so on. I thought it was good to highlight some of these concepts. When it comes to the essence and the scope of this FE-Sludge project, in practice, we are looking to an operational concept that allow industrial wastewater treatment to save energy, save chemicals, while generating biogas. So it combines these three aspects of the energy demand of the wastewater treatment, the chemical needed to process the wastewater, and use wastewater also for biogas production. If we look to the wastewater treatment as such, is very similar to a municipal wastewater treatment. So we have the incoming wastewater with some preliminary clarification, and then the key process that is the activated sludge treatment. The problem and the difference is that when we're processing industrial wastewater, usually could be very specific in composition. And if we take the pulp and paper industry, we basically find a lot of carbon, but no nitrogen, phosphorus in the wastewater treatment as such. Therefore, the nitrogen and phosphorus has to be added into the system to support the activity in the activated sludge treatment. And that's where FE-Sludge is looking at. How can we impact, reduce, or change the amount of chemical going to the system? And at the same time, how can we optimize the activated sludge treatment so to reduce the energy demand? As someone said before, is probably valid also for municipal wastewater treatment, but even more for industrial treatment. Operational of today of this type of units tend to minimize the amount of sludge that is produced. As a consequence, there is high aeration, prolonged time, and sludge age that is over 14 to 17 days. Which, of course, that's the main reason of that is that they reduce the amount of sludge that they need to dispose. The concept that we are implementing is to include in different parts of the wastewater treatment the anaerobic digestion concept. The first one is using a high rate reactor or USB that is processing the raw wastewater after primary clarification. So we take the biogas from the soluble COD. By doing this, we reduce by 50% roughly the amount of soluble COD that is supposed to go in the activated sludge treatment. At the same time, we include a more conventional anaerobic digestion unit that is processing waste activated sludge together with external biomass. In the specific case is fish waste. So we combine a co-digestion of fish waste and waste activated sludge. By doing this, especially thanks to the fish waste, we are bringing into the system a significant amount of nitrogen and phosphorus, mainly nitrogen. This nitrogen, after the anaerobic digestion, is still in the system in the reject water. After the watering, you have the solid part that could become a fertilizer, but you still have the reject water stream that is high in nitrogen. And this nitrogen in the FE-Sludge concept become basically the replacement of what we were using as a chemical addition before. So the nitrogen here is a return into the wastewater treatment, replacing external nitrogen. And there are also some adjustment of the operational in the activated sludge system with the target to reduce the sludge age from the 17 previous condition, 17 days, to below 10 days. In this way, there would be higher volume of sludge produced with also a better digestibility property. So that's why it would make more sense, given the fact that we can process the waste activated sludge for biogas production. It makes more sense to optimize the activated sludge system so we have more sludge rather than less sludge. The key partner involved is the Norske Skog pulp and paper industry located in Norway. They have a few plants in Europe and some plants also in Australia. And this is one of the largest mills in Europe for production of newsprint. So their wastewater treatment is processing 20,000 cubes per day. The biogas part is processed by Biokraft, which is a sister company of Scandinavian Biogas. And this all new plant has been built not only for the scope of FE sludge. FE sludge came sort of on top of this for a demonstration of the integration between the wastewater and the biogas plant. I think that's another nice overview where you see the wastewater treatment. Here's the aerobic base divided in different sectors. That's the secondary clarifier. And just by the shore and in between tanks, it was possible to fit in a large biogas plant that is treating food waste, sewage from the mill, and with the biogas production up to 125 gigawatt hour.
Francesco, you have 1 minute more.
Yeah, that's perfect. If we look quickly to the mass balance, in the base case, the amount of nitrogen added externally was over 700 kilo per day. With the FE sludge condition, we assume that the nitrogen will basically reduce to zero, but we still might need some phosphorus to be added. Looking at last year urea dosing, that's the way that nitrogen is produced. We achieved by the end of last year about 90% saving. During this year, we are not yet under this condition. We had to stop the site a few times, and even the mill closed production for a few weeks. So it has been a little bit up and down, but we are soon able to go back to this 90% nitrogen dosing. Last two slides. As I said, the CO2 emission is the main driving force of the project, and by implementing it, we assume and we expect it to reduce and go from 1.4 kilo CO2 per cubic meter wastewater to below 1. That comes to almost 3.5 million CO2 saving per year. The project is still ongoing, but we have a nice event where we enter more in details and in November, so you're all very welcome to participate. And thanks for your time.
Thank you very much, Francesco, and congratulations, because of course the challenge in your case is also huge, and you managed well despite all the different constraints. And as I mentioned at the very beginning, Sweden is a key player in biogas production. So congratulations, and happy to have you here. And of course, we will share probably in the future some other webinar presentations and also nice talks about future projects.
Thank you.
Thank you very much. So let's move now to David Fernandez, that will talk about EcoGate. EU supports the first biomethane injection into the Spanish distribution grid. So please, David, you have 10 minutes to highlight the main outputs of your project. Thank you.
Okay, great, Jose. Good morning, everyone. I will try to share my screen. Okay, please, perfect. Could you confirm to me? You can see my screen?
Yes, wonderful.
Okay,
David.
Perfect. Thank you, Jose. Okay, so good morning, everyone. Thank you to the organization for giving us the opportunity to share with you the the development of this European consortium. And thank you all of you, all the attendants, for your assistance, and of course all your questions or comments will be very welcome at the end, or not at the end. If you want, you can interrupt to me. Okay, so here we are to show you the developments of the EcoGate, the European consortium, in which the European Union supports the first biomethane injection into the Spanish distribution grid. My name is David Fernandez, the director of the consortium. And, okay, here we are the partners of the consortium. We are a huge consortium with 38 companies and organisms from four countries of the European Union, from Spain, from Portugal, from France, and from Germany. Actually, we are a very multidisciplinary and complementary competent consortium due to the fact that all of our partners are from the beginning of the value chain in the gas operators, in which is energía. In this case, is my company, in which is the leader of the consortium. And we have technology and service providers, as you can see in the chart, and of course we have end users of this energy, support by partners that have a great experience in market knowledge and in the dissemination results of the project. Moreover, the EcoGate, the consortium, has a very important stakeholders support. 39 companies and organisms from the four countries, haulier companies, all type of associations, vehicle manufacturers, biomethane producers, technological centers. In this case, we want to highlight the support of the Ministry of Spain, the Industry Ministry, and the same in Portugal, in the Direção-Geral de Energia e Geologia. Our overall objective is study the conventional renewable gas market in the main corridors of the European Union. We are talking about the Atlantic corridor, the Spanish Mediterranean corridor. Through new technologies and innovative solutions for supply logistics services, cleaner fuel composition, refueling infrastructure, vehicle and components manufacturers, and all the global operational process. More in detail, our specific objectives are the deployment of an European-wide network of 21 LCNG refueling stations in Portugal, Spain, France, and Germany, located in strategical points in the Atlantic corridor from Portugal, Spain, and France, in the connection with the Atlantic corridor with the Ring-Danube corridor in Hildesheim in Germany, and all along the Spanish Mediterranean corridor. And the deployment of one biomethane supply point in the Atlantic corridor in Madrid, one HCNG supply point in the Atlantic corridor, in this case in Burgos, north of Spain, introducing and implementing 14 advanced and innovative solutions on the LCNG infrastructure, vehicles, and natural gas logistics services. Now we can see the map of the refueling station, the 21 LCNG, the biomethane plant flagged in green in Madrid, and the 8 CNG plant flagged in gray in Burgos. Okay, so let's talk about the project of the biomethane plant. This project is based in 3 main objectives. The biomethane injected into natural gas distribution network, the development of the guarantees of origin for renewable gas in Spain, and the demonstration of the eco-efficiency of renewable gas for mobility. Here you can see the plan of the biogas and the biomethane production in the water waste treatment plant in Butarque, in the south of Madrid. We have obviously a biogas plant, a wastewater treatment plant of Canal Isabel II, an upgrading plant with a mines and process analyzers and the chromatograph. The biomethane injected into the natural gas distribution network by 5 gigawatts hour a year. The guarantees of origin for renewable gas of this biomethane injected into the gas grid, and the bio-CNG refueling station connected to the natural gas network with a tank of 1,920 liters by 250 bar. Here you can see the screen of the production, the injection of the biomethane into the gas grid, and obviously in the gas grid injection, you can use the biomethane for all the traditional uses and users, as domestic ones, commercial ones, industrial ones, and obviously for mobility. Here you can see the plant. At the bottom of the digesters of the plant, and the rest of the facility. Here you can see the pipes of the connection between the digesters with the biogas, which is flowed from the digesters to the upgrading plant. Here in the plant, we see in a black color. This is the upgrading plant with the pipe connections, and here you can see the injection plant in white, with the injection pipe into the gas grid flagged in green, and after that we can see the bio-CNG refueling station connected into the gas grid through this pipe connection flagged in green, and this is the refueling station. Okay, as we can see before, one of the first objectives of this project is the biomethane injected into the natural gas network. Here we can see the situation of the biomethane plants injecting into the gas grid in Europe in 2013 and in 2017. Obviously, we can see the very interesting progress of in Germany and in Sweden. But more than this, we can highlight the situation of Spain. In Spain, in 2013, we have only one plant of biomethane injecting into the gas grid, and in the end of the 2017, we can see Spain remains one plant, the same one. So, moreover than that, the most interesting thing here is to show as countries as France, Denmark, or UK have in 2013 3, 4, and 6 plants, more similar than the Spain one, and after 4 years, they have the development, a great development with 22, 30, and 85 biomethane plants injected into the gas grid. So,
excuse me, David, 1 minute more.
Okay, thank you. So we can see that if we want, if we work harder, we can develop the market of the biomethane in a country. Obviously, as we have said, in October of 2019, we can achieve the EcoGate Edar Butarque, the second biomethane plant in Spain, injecting into the gas grid. The second objective was the deployment of the guarantees of origin for renewable gas in Spain. We have developed a model proposal for the certificate of origin in a voluntary scheme, support and co-elaborated with the European Renewable Gas Registry, ERGAR, and we have a very important Spanish support as the Spanish Biogas Association, the Iberian Association of Natural and Renewable Gas for Mobility, and the Spanish Water Supply and Sanitation Association. Now we are in the process for presenting the proposal to the ministry to help us to achieve the mandatory of the RED II. And the last one, last but not least, objective, the eco-efficiency of biomethane for mobility. This is the greenhouse gas emission in a well-to-wheel sense, elaborated by the European Commission, in this case by the Joint Research Center. And here we can see that biomethane, bio-CNG, is the better energy, traditional energy or renewable energy for reduction of the CO2 footprint in a well-to-wheel sense. Here you can say that there's no other energy that has a better GHG emission reduction as the bio-CNG. Obviously, if you can consider the life cycle assessment, a cradle to grave sense, and obviously these results will be improved by the biomethane due to their contribution to the circular economy. And this is a brief highlight of our project. So thank you for your kind attention. And
thank you very much, David. And it's impressive the effort you did and what an amazing team you build up with so many partners. And I'm glad to see these joint forces to really make it through this important challenge, as you claimed, with that low GHG impact, no, which is very important for our carbon neutrality objective.
Yes, we are really proud of our work, and we are disposal to share our results with all.
Perfect. Thank you very much. So let's jump now to John Chamberlain, which is the biggest senior expert, probably one of the biggest experts in the world when dealing with biomethane. So please, John, tell us a bit more about the unidad mixta, the gas renovable you build up, and that is an example of circular economy.
Well, thank you for that introduction. I'm not sure it's correct. Good morning, everybody. My name is John Chamberlain from the Innovation Department of Naturgy, and I have a certain responsibility for the renewable gas natural projects. In that reason, I participated with Carmen in the LIFE project, and now I'd like to present what we call the project, the Unidad Mixta of Gas Renovable. It's a public-private collaboration that has been driven forward to promote renewable natural gas. Before I start, I'd just like to hope and wish that everyone is well in these strange and challenging times. So, like all projects you do on renewable gas, on biomethane, they have to be good collaborations, you need strong partners, and in this case, in this project, the partnership has been between Naturgy and Energy Lab. Energy Lab is a technology center located in Galicia, and they've done the scientific work. Naturgy has been more responsible for the industrial work. The project is financed for the Galician local area in the game, Por Gain. It's a local funding mechanism, which we are truly grateful. And although not a partner, a former partner, the project really does have a partner in the wastewater treatment plant of Benz. They have been the hosts of the industrial sites, and their active participation has permitted the successful completion of the project. The Unidad Mixta, this public-private partnership, really was another project of the Naturgy portfolio to develop biomethane, to act as a demonstration project in Spain to show that the technology was possible. Also, in this particular case, it was a project that permitted us to understand the costs, and I would dare say that the plant installed is a bit more experimental than in the LIFE Methamorphosis project and maybe in the Butaki project. So we've been able to play around with the different parameters a bit more. But the idea here is we take, in the wastewater treatment plant, they produce sludges. These sludges go through an anaerobic digestion process, and they produce biogas. 3/4 of that biogas, roughly, is used by the wastewater treatment plant for their own energy and heat needs, but they have a quarter that they didn't use. And this was actually flared. So we have taken that quarter, we moved it into biomethane to get a quality product that is equivalent to natural gas, and used it for the mobility demonstration. So if we look at the objective of the plant, in first place, we looked at the production of biogas. That was done in a laboratory scale in Energy Lab, and we looked at ways and additives that you could improve performance. In the wastewater treatment plant, which is what the slide shows, we conceived the project in 2 phases: a membrane separation to produce biomethane, and then a biomethanation reactor, which is put there in the long hydrogenotropicus. Using hydrogenotropicus, to carry out a biological methanation of the CO2 to produce methane. So the first phase was membranes, the second phase was biocatalytic methanation. So if we move on, these conceptual schemes show just simply the idea of the plant. We decided to install the experimental center, or the biomethane production center, next door to the gas meter, the gas storage vessel, and you see the picture of that and the schematic complex of the membrane biomethane upgrading plant. The real picture is shown in the following image, and this is the plant we installed. It's around half the size of the LIFE Methamorphosis project, treating 100 cubic meters hours of biogas to produce around 60 meters cubed of biomethane. The difference to the metamorphosis plant is we've got a bit more flexibility in how we operate it. We have the capacity to run it in with 3 stages of membranes, with 2 stages of membranes, and to play around a lot more. It was conceived as more of an experimental facility to improve our understanding of the process. But the concept is exactly the same as Carmen showed in her previous presentation of the Methago project. From the biomethane within the context of the project, from the biomethane produced, we've used it to fuel various vehicles. So being in a wastewater treatment plant and where it was, we actually had to construct a line of around half a kilometer from the biomethane plant to a little local refueling facility so that we could refuel vehicles. A very small scale, but it was there for the demonstration. And that has been used to fuel a public autobus, a public bus, which is functioning every day on a commercial route in A Coruña, and to fuel various vehicles of the wastewater treatment plant. And I think one of the most important messages to say in this, and I think it came out of the Methago project with the SEAT vehicle that completed 100,000 kilometers. With the right treatment in the upgrading plant, we are producing a biomethane of adequate quality for gas injection. And this biomethane can happily be used as a biofuel for vehicles, and its performance and operation is the same as natural gas, and we have not seen any negative effects. This obviously goes in alignment that we are obtaining a biomethane of over 95% purity. We are treating all the silothenes and sulfur contents before and removing them. But the quality we've managed to get in the projects has been successful for the demonstration. The bus I think has nearly done 100,000 kilometers as well in these transports. If we look to the second phase of the project, because the membranes was maybe the first phase, we've looked at two other areas, the biological methane plant and then the future injection of the biomethane into the gas grid. So if we look at the biomethane methanation reaction, which is a lot more experimental, it's one of the biggest reactors in Europe, I think, for the context. We've constructed a reactor that uses methanogenic archaeas. These are species, they're single cell species, I'm going to use the word species, that you can find in nature, you can find them in the digestive systems of animals, and you can find them in the swamps. And they produce methane. They react CO2 with hydrogen, producing methane. And what we want to do here is to see if we can use these species to produce a methane quality of sufficient quality for gas injection or vehicular use. Here, the in-feed is hydrogen and CO2 that we take off the biomethane upgrading plant, or even biogas. Our desire here is to be able to inject biogas with a bit of pre-treatment and convert it all into methane, like a second level technology of biomethane. These experiments have only really just started. They're undergoing as we speak now, but the results are interesting, we shall say. So we are continuing with these experiments. I don't need to go into anything. The reason we've gone for the biological methanation process instead of the chemical methanation process is that potentially, if successful, it will have a lower energy demand and therefore be more competitive. So in conclusion, the other area which I haven't mentioned, I haven't really had time to mention, is the gas injection, which we hope to be injecting at the end of the year. So in conclusion for the project, I think the first thing to say is that the project was a success. I have my thanks to all the partners. We demonstrated that the biogas produced in the wastewater treatment plant can go to a biomethane quality, can be injected into the gas grid, and can be used as a product fuel for things. We understand the whole framework from this project, from the LIFE Methamorphosis projects, of what business models and business cases need to be done in Spain for their implication. As David says, we will need a certification system for the guarantees of origin to make a business model for biomethane. Because the truth be told, This industry has not taken off in Spain because it hasn't had the help and support that it's had in other countries. And what we hope to use with all these projects is to have a demonstration that the technology is possible, it is sustainable. This wastewater treatment plant in Galicia is a perfect example of the circular economy, sorry, and it is the way forward we need to go as we go down the decarbonization route to the future. And with that, I'm not sure if I've overrun on time. I would like to
John, 10 minutes
goodbye.
Exactly. So thank you very much, John. You did a very good presentation, and I like that you enjoy playing with biology, because of course my background is in bioprocesses, and the biology has been doing innovation for thousands and probably more than thousands of years. So they will probably be much more efficient than us. So congratulations for your initiative and.
Well, thank you, Jose, but I'm a chemist, so I'm going to protect the chemical route, not the biological route.
Yeah, because the biological route always arises questions and doubts and surprises, but it's our day by day. So let's move now to our last speaker before the question section, and I welcome Sunil Arhandas from our friend company FCC Environment, that will talk about the possibilities to harvest biofuel in landfill. So please, Sunil, the floor is yours.
Hello, I'm going to share my screen. Can you see the presentation?
Perfectly.
Okay. Hello, everyone. My name is Sunil Arhandas. I work for FCC Environment as on-site project management of the project LIFE Landfill Biofuel and two other LIFE projects, LIFE for Field and LIFE Blast Mix, which the main objective of these two last projects is to recover and recycle PF field and mixed plastic fresh. I would like to thank the Metamorphosis Project events to invite me to this event and the other assistant to join us in this presentation. Before the start, I want to say that my technical English is, I think, is not good enough, so I will try to do my best. I'm sorry for the mistake I can make. So let's move on. Okay, LIFE landfill biofuel process consisting in capturing the gas emission of the decomposition of the organic waste that otherwise will be emitted to the atmosphere. This biogas will be destined to put the purification process and transport into a biomethane, which will be used as fuel in heavy and light vehicles. The project will be placed in Granada province, specifically in a town named Alendín, where is placed the Eco-Central plant. This plant manages around 350,000 tons of waste from municipal solid waste and around 10,000 tons of packaging waste, as well known as the yellow container. The Eco-Central landfill is on service from early 80s, more or less. So the amount of waste that is in landfill in it is a lot. Before I start talking of the main objective of the project, I think it's necessary to know some background of the way that a landfill is managed. Previously, the 60 or 70% of municipal solid waste in Spain end up in landfill. The most abundant waste in this fraction is the organic fraction. Nowadays there are a lot of technologies that can treat this organic fraction. Composting could be the most extended method. There are many landfills in Spain where the organic waste reach in the landfill in a not stabilized way. starting after a few years an anaerobic digestion process. This process generates biogas composed mainly of CH4 and carbon dioxide. Disgassing is carried out in the majority of Spain's landfill to avoid the discharge of CH4 to the atmosphere. As you know, this gas, the CH4, is a very high greenhouse effect potential, more or less about 7 to 10 times more than the carbon dioxide. The disgassing of the landfill consists more or less in a network of connected cells and pipes that, by applying a depression, lead the biogas to a treatment plant. In some facilities, this gas is used to burn in a flame, but in others, more advantage, like for example, Ecocentral, this gas is used to feed a cogeneration engine to generate electricity. In this way, we can use in Ecocentral, we can use all our equipment with energy that is a green energy. I would like to say that the landfill biogas composition is CH4, carbon dioxide, and it depends on how we do the maintenance of the landfill, quantity of atmospheric air, and others like siloxane. Now, yes, the main objective of the landfill biofuel is to demonstrate a cost-effective and comprehensive solution for the implementation of the waste cell to improve the production and recovery of landfill biogas with the application of innovative biogas improvement technology, combining membrane filtration and BPSA system to use as fuel in light and heavy vehicles. This is more simply that we can write. What we want to know is to take the biogas generated in the landfill to upgrade, to make biomethane to use for fuel for light and heavy vehicles. The specific objective of this project will be the reduction of carbon dioxide emissions by 90% and NOx emission in 98% compared with diesel vehicles. To improve the recovery of the biogas, to improve the recovery of biogas from the landfill to avoid the presence of atmospheric air. As I say, the problem with our biogas of the landfill is the presence of atmospheric air that could be more or less represent 4 or 5%. Another specific objective is to encourage the deployment of the new concept of circular economy as more of the LIFE project, the job creation, and to improve the competitiveness in the waste sector. As I think, as all you know, the LIFE project had to be structured by a consortium formed by different enterprises. In this case, FCC Environment will be the project coordinator. As you know, FCC is a world leader environment service. It has been serving for more than 150 years. We can process more or less 24.5 million tons of waste. In this project, a part of being the project coordinator, will be the responsible of work with the upgrading plan, the buying a heavy waste gas collection vehicle, and to provide the project with landfill biogas. The other partners of the project are CARTIF. CARTIF is a technology center dedicated to research and development. The responsibility of this enterprise in this project is to check and certify the quality of the biomethane generated after the upgrading. Evento and SEAT, they don't need a presentation. Evento will be the responsible of verify the biomethane generated in the facility in a track from FCC. And SEAT will provide 3 light vehicles to test it. SEAT is going to run more or less 140,000 kilometers per year. The rest of the partners are Universidad de Granada. Universidad de Granada will be responsible of the characterization of the quality of the biogas from the landfill. GasNam is an association that promotes the use of natural gas, and it is responsible in the project of the communication. CISAS Bank is one of the most important technological enterprise in gas purification and will be responsible for the development, design, and construction of the landfill gas purification pilot plant.
1 minute more, Sunil.
Okay. I'm going to go faster. In this slide, I will only say that the project has a duration about 4 years. The project has started on July of the last year, and the end will be estimated in June of 2023. At this point, we have already done most of the biogas characterization. That allowed us to have a detailed profile of the landfill biogas and how the atmospheric change could modify the composition of our biogas. And the budget, the estimate budget for this project is 4.4 million euros, which the European Union contribution is about 2.3 million. The rest of the budget must be provided by the other project partners. And in conclusions, I would like to say that this project is going to, we would like to promote the circular economy. We would like to reduce the greenhouse emissions to the atmosphere, and we would like to use a renewable energy source generated from waste. And thank you for everything.
Perfect, Sunil. Thank you very much, and thanks to the 4 speakers, because I think we saw what are the possibilities to harvest biomethane further from our wastes, and it's very important, and I think it's key in this actual context where we want to decarbonize our economy. So please now the floor is open for questions, so raise your hands, and we have some minutes to take advantage of these 4 impressive panelists we have. So all the questions and concerns you have about biomethane, don't hesitate to jump in and bring them. I will first start. So Francesco, I like pretty much your approach, and I've seen a couple of very nice even IH 2020 projects where there are these symbioses between different partners and between different entities. In your case, I think it's pretty impressive to mix wastes or sludges from different origins to somehow balance the nutrients and make the trick incorporating anaerobic processes into the aerobic typical treatment train. How do you see it under our replication point of view? Do you see it easy to replicate? Because I've seen, especially in the north, so in Sweden, the Netherlands, and more in northern countries, that there is this kind of cooperation between different sectors and between different entities. I don't know how is your replication plan for your project in the future?
Yeah, the afterlife plan.
Exactly.
But that's a good question. It's a building up process. Our target is, of course, at the moment still the pulp and paper industry, because we see there the potential of being able to make this good integration. It could be, as in the Norwegian situation, where there is a new plant from scratch, from the biogas perspective, that is located next to a pulp and paper industry, and there is enough external biomass that can provide a nutrient. Great. But it could also be of nearby location where at the moment, for example, the reject water is just put in the sewage, but it could be redirected to a nearby pulp and paper industry. With the fish waste, of course, that works very well because it's high in nitrogen. But if we look to similar type of biomass, we see that some manure, for example, for chicken manure or pigs, the amount of nitrogen is comparable to what you can find in fish. So that could be another type of valuable substrate for this type of integration.
Mm-hmm. Yeah.
For the project, I just conclude to say that it was, of course, a breakthrough already to get the pulp and paper mill allowing in their premises to construct a biogas plant and accept external waste. That's a sort of mind shift that's happened in the last 5 years and is already sort of expanding in the Nordic.
Okay, yeah, I like this approach, and probably we need to move to intelligent or smart industrial platforms, no, where you collect together different industries, but that it makes sense to somehow cross-link all the different partners there. So there is this kind of symbiosis between them, no. I know it's moving somehow in the northern countries, and I think it's something we should bring to the southern ones. So I like this approach, and probably the problem for one entity is the solution for the other one. So I like this approach. Thank you very much, and congratulations. Please, don't be shy. I don't see anyone raising the hand, so I will go on, but please bring your questions. So for David, you know, in Aqualia, we run a lot of wastewater treatment plants, and in most of them, when there is an anaerobic digester, we use the biogas to burn it into a CHP and to get electricity back, because we need it to provide oxygen within this old-fashioned activated sludge process. So how do you see your niche or your opportunity for the biomethane use, and how can it somehow, or will it compete with the CHP with electricity production, or do you see it as a complementary tool? You need to unmute your microphone. Excuse me, we don't hear you. if there is a microphone sign somewhere, and
now,
okay.
So I think we must see with holistic view. So we obviously have a great challenge with the decarbonization economy. And one of the first steps for that is the efficiency. Instead, the energy efficiency. So in this, it's obvious that the use of the biogas for producing biomethane is more efficient than the use in a CHP. So in terms of energy efficiency, I think we must to do this gap and launch the second part of this evolution. I think the first evolution of the biogas in a CHP is a great evolution, but now we need a higher level. We need to take advantage of the new technologies, and we need to take this biogas to produce biomethane for all the traditional end users.
Perfect. No, I totally agree with you. And I will tell my engineering team that for the future wastewater treatment plant, we should consider this option instead of buying a couple of CHPs. I totally agree with you. And I also believe that the decarbonization and global emissions are important. So I believe there is better uses of this bioenergy source. Perfect.
Yeah.
Okay, we are running out of time, but I have one question for John. Of course, John, I pretty much appreciate, as I said before, the bioprocess. Where are you planning, or from which source are you planning to harvest your H2, your hydrogen, to somehow help your bugs to convert the CO2 into methane, probably from water electrolysis, no?
Well, thank you for the question. I think the hydrogen source is actually not the big question in methanation. We have to demonstrate the concept, and we have to make sure it's upscalable. Initially in this project, the first trials are using bottled hydrogen, but we will be putting an electrolyzer on site to produce green hydrogen if we say that it comes from a renewable source. But the key question here is more that if we can use the process to get a high-grade biomethane. That is the key issue, more so than where the hydrogen is coming from the moment. The hydrogen source will be part of the final cost equation in the business model. But the big challenges for methanation is demonstrate the final gas quality, demonstrate that you can scale it up, and it can be competitive.
Perfect. Yeah, I mean, there is a lot of noise now with hydrogen. And I know, for example, that our head in the innovation department, Frank Rogala, is a bit afraid of hydrogen because he remembers that many years ago in Germany, there was a big problem with a big balloon that exploded that was fueled with hydrogen. But probably we have already overcome all these technical issues, and hydrogen will play for sure an important role in the future of the
I think, Jose, we have to move on from hydrogen explosions. I think the key issue here is that if the world or if Europe wants to decarbonize, electrification is not enough. You need a portfolio of solutions, and you need renewable gases, and they will be 10, 11% of the final solution. So to a decarbonized world, we need renewable gases. Like hydrogen or biogases.
Perfect. So let's move on because we are a bit late according to our schedule. Someone willing to close the question section? I was the only one asking questions. So please, for the next session, I hope someone else will bring its view. So let's move now from the biomethane, and thank you a lot for the 4 speakers. I think it was very interesting. And let's move now to the other part of the equation within this LIFE Methamorphosis ambitious project, which is wastewater. So thank you for the 4 coming panelists. And we start with Maria del Mar Micó from Acciona, that will tell us about the Life Celsius project and how they developed sustainable strategies for urban wastewater treatment in warm climates. So please, Maria del Mar, the floor is yours.
Hello again. Thank you very much for the opportunity you give me to tell you the highlights of our Life Celsius project. Let I share the presentation. So as you introduced, we were more focused on the development of a holistic wastewater treatment that include a step of anaerobic digestion that aligned with your interest in biogas production. It was a project also funded by LIFE program. It took place in Murcia, in the south of Spain, in a Chena wastewater treatment plant, which is a medium-sized wastewater treatment plant with conventional pretreatment and secondary treatment, And the idea was to treat the sandy influent of the wastewater treatment plant through our technology proposal. It was a very small consortium. In this case, we were the technical and coordination responsibles, and we were collaborating with the Agencia EFE, which was in charge of dissemination of the results. So the main issue that was addressed by Celsius project was the eutrophication problem, which is an issue all around the world, especially in coastal areas, and is related to the introduction in the aquatic media of external nutrients such as phosphorus or nitrogen, but also organic matter. These nutrients provoke the blooming of algae or bacteria that consume the oxygen in the aquatic mass we were talking about, and causes disruption of the ecosystem. Also, but others problems in further treatment, for example, for making that water drinkable, etc. That oxygen consumption is not only provoked by that bloom, but also by its decay, because the bacteria that take rid of the decaying biomass also consume that oxygen, exacerbating the problem. Sometimes the eutrophication is caused by natural causes such as runoff or similar, but there are also evidences that poorly wastewater effluents can also cause this entering of nutrients in the media. This is why LIFE Celsius project will be focused on ensuring that wastewater treatment, avoiding the introduction of this nutrient in the media. In fact, in Spain there is a very well-known legislation regarding this issue from 1985, which limit the emission of these nutrients by the effluent of wastewater treatment plants. The fact that we choose Murcia to perform this project is related to the fact that Murcia has important eutrophicated zones, such as La Manga del Mar Menor, which is an important environmental asset to Murcia, and also the river mouth of Segura River, which is located in Alicante, not really in Murcia, but is related to the region by the fact that all the Segura River comes all its way through the region of Murcia. Another issue that LIFE Celsius project addresses is the energy consumption related to wastewater treatment. More than 50% of the energy consumption of conventional treatments are devoted precisely to the elimination of that organic matter and nitrogen compounds present on wastewater. So it is logic that new tendencies or new trends in wastewater treatment will be focused on reducing this energy consumption and breaking the water energy nexus. So the objective of this project, as I told you, was to reduce the energy consumption by wastewater treatment and reduce the greenhouse gases emissions related to that wastewater treatment. Also reduce the pollution related to that organic matter and that nitrogen compounds that not always are comprehensively treated, and reduce the hypoxia and eutrophication issues related to wastewater treatment. We also try to study the scalability of this technology, and we make a special effort to transfer the knowledge to the stakeholders that could use it for policy making or technical decisions in wastewater treatment plants. So we propose a two-step process. The first one is an anaerobic membrane reactor. The difference between this anaerobic membrane reactor and other anaerobic devices that were commented during the workshop is the fact that we were talking about mainstream, about wastewater treatment plant, wastewater influent, which is much lower concentrated in organic matter So the challenge will be to obtain the most of that diluted influent. We choose the use of anaerobic membrane because we have the lack of aeration, so we have an important energy reduction in this from this perspective, and it also has a low sludge production related. So it is not one of the main objectives of the project, but it's also an advantage of this kind of processes. And as I told you, also we have the opportunity to produce a biogas that could be valorized within or out of the wastewater treatment. The second step was focused on remove the nitrogen compounds that were not affected by the anaerobic previous step. We were thinking of a partial nitrification combined with anamox. As was mentioned at the beginning of the workshop by Carlos, the first step was focused on converting part of the ammonia into nitrite. And the second one, anamox, combined the nitrite with the non-converted ammonia to generate nitrogen gas. The challenge here, compared to the Elan process, is that here we are talking again about mainstream, which much lower concentration of nitrogen that the Elan process is used to deal with. So in this case, also we have an important aeration reduction. We will see why, related to the partial nitrification. No external organic matter is needed in the case of anamox. In the nitrification in conventional system, you usually need to add external organic matter in the shape of methanol or other substances, or you need to increase recirculations inside your plants in order to give biodegradable matter to that denitrification step that we are skipping here. And as well as we are working with lower oxygen consumption technologies, or not even any oxygen is needed for anamox, the sludge production is also lower than conventional system, and it can be also an advantage for this technology. The first step of organic removal by means of an NDR was due in this system, and quite small compared to the previous project, but quite hard to manage system of only 5 cubic meters of digester. And the particularity compared to other projects is we were testing a pretty particular membrane system based on ceramic microfiltration by means of a Grundfos biobooster that was based on discs that cycle around a coaxial engine. So the results in the NMDR were not as positive as we expected, because our influence was highly concentrated in sulfates, and that sulfates promotes the degradation, the generation of sulfite-reducing bacteria, which were able to degrade organic matter, but were not as efficient as expected by an anaerobic consortium and a conventional anaerobic consortium. So we obtained low organic matter removal and low methane concentration in our biogas. It was due to the fact that these bacteria compete with the substrate in every step of the anaerobic digestion, and also the generated hydrogen sulfide inhibit the methanogen activity. So the results obtained in this step were not as good as we expected. However, with experimental results, we were able to modeling the process in the case we have a more convenient influent, and we were able to obtain mathematical modeling to help our engineers for scaling up the process and propose real scale solutions for further bits and further new wastewater treatment plants. The thing that we were using, we focused our project in warm climate, was the fact that we were able to work with psychrophilic temperatures, but quite close to mesophilic temperatures, so no need for external heating was needed in this case. In the case of partial nitrification on amox, these were two pictures of the pilot plan we were using. These are the sizes of the pilot plan: 1 cubic meter for partial nitrification and a little bit smaller for the two different anamox growth we were testing. We test a biofilter, quite small, 25 liters biofilter, and a granular system of half cubic meter. The flows also
1
decreased.
minute more.
Okay, sorry, I will run a little bit. I will fast a little bit. So the idea here in the partial nitrification anamox was to reduce oxygen by a short circuit within the nitrogen cycle. We reduced the oxygen just talking about the fact that we were converting ammonia only to nitrite instead of nitrate, and only half of the ammonia has to be converted for the metabolism of anamox bacteria. So we were able to save 45% of energy and also aeration, and also GHG related to this energy. We were able to test oxygen control strategy to effectively control partial nitration, which is like the bottleneck of these kind of systems. We were able to test it experimentally and also modeling it mathematically. In the case of anamox, we tested both, as I told you, we tested both two different growth system. In the case of the biofilter, we obtained a very good quality effluent and a very sturdy and robust system that could cope even with COD spills coming from the previous COD removal step. We also achieved very high nitrogen removal rates, which were sustained around 6 grams per cubic meter, but we achieved double rates in some seasons. In the case of the granular reactor, we could check the COD effect in this kind of anamox growth. We see that in the case of acute exposure, the nitrification did not overcome the anamox process, but in the case of chronic exposure, the denitrification took more and more importance in the whole project, in the whole process. However, the effluent quality was still acceptable. So our main conclusions during the process in highlights is what we were able to mathematic modeling the MDA and MBR in order to help scaling up of the technology. Also, we tested a pretty particular system of microfiltration. Partial nitration was also able, in partial nitration, we're also able to test the advanced aeration control that helped us to obtain a stable process, which was harder than in the case of side stream systems due to that lack of richness in nitrogen, as I mentioned before. The anamox filter showed to be the most robust and interesting technology for this kind of anamox application, despite the fact we were able to obtain a granular anamox system, where we were able to study the effect of COD spills. Our next step, our focus on improving that partial nitration control by new strategies in a new project called esta, which is funded by CDETI, and is the project we are focusing right now relating this kind of wastewater treatment integration. Thank you very much, and I will be open to any of the questions you may have. Thank you very much again.
Thank you very much, Maria, and congratulations for also a very ambitious and complex with advanced bioprocesses, trying again to get rid of the old activated sludge process that has been used for the last more than 100 years. Okay, so let's stay now in the anamox world, which is of course my loved world, since I grew up within this Anamox experience. And now Jesus Colprim will move from Maria del Mar, that was talking about urban wastewater and rather diluted streams to much more concentrated streams. And Jesus will tell us about his wide experience in Anamox use in landfill leachate treatment. Please, Jesus.
Okay, thank you very much, Jose Ramon, for presenting me, and I will present you our experience in the Anamox technology, but in the leachate. So just a minute, can you see the slide, the presentation?
Yes,
yeah?
Perfectly.
Perfect. Okay. So first of all, in our case, we will present the Anamox process that is basically a biological treatment for the leachate.
We lost Jesus, no? It looks like. Are you listening? Something?
No, I'm not.
No.
No. So we lost Jesus. Let's wait 1 minute if we are able to have him again. Otherwise, we will move to the next speaker, and when Jesus is back, we'll bring his chance again. Let's wait for a minute if Jesus is able to come back. Everything was going smoothly, so it was strange with these virtual events. There are always some technical issues, and of course we need to rely on the internet connection.
I'm here
Hello,
again.
Jesus. Okay, wonderful.
I'm so sorry.
We lost you for a couple of minutes, so please start again.
But I'm so sorry. But anyway, I will continue. Okay, I was talking about the conventional treatment, and that can be by means of biological process, but also by means of some chemical treatments. But all of them, there is a high cost for this treatment of leachate, right? So one option is, or can be, to try to move to alternative treatment. No? So the classical nitrogen removal and ammonia stripping, by ammonia stripping can be used or can be moved to a combined partial matification and Anamox process. That means a two-step process. But also the refractory COD by means of reverse osmosis can be changed to the classical photophantom process or advanced oxidation process in order to give a suitable effluent, right? So my idea is just to explain you our experience in the Corsa landfill, but not only in the Corsa landfill side, but our experience over the last 20 years with this technology. So, but if we move to, or we look at the Corsa case study, initially there was a phantom process for the organic matter removal, and then was followed by a stripping process where the ammonium was recovered in form of salt of ammonium sulfate. So this was the original alternative in the process. No? So they tried to move that into a biological process, basically because of the cost of the process. We have a high cost in the regions of the process, but also in the management of the leachate, because in spite that you are able to recover ammonia in the form of a ammonium sulfate solution, it's really sometimes difficult to introduce into the market. So the management cost of this effluent sometimes is really, really high. So our idea was to try to move the stripping and ammonia recovery in form of ammonium sulfate for a biological process with the partial nitrification and anamox in a two-stage process. So this is basically the process that we have implemented. And what we have is that first we have some conditioning of the leachate, then we have the partial nitrification, and then we have the anamox reactor. All of them, both reactors working in SBR model. So this is the final plan that we have, and this is mainly focused only for biodegradable organic matter removal and also for the nitrogen removal in the anamox technology. Of course, the refractory organic matter then will be used, will be removed in the Fenton process that was already installed. But in fact, this biological process is what we say the Panamox technology. Okay, so this is not a plan that we have constructed from one day to the other. So it's a 20 years experience that we start from the lab scale to the full scale. And I would like also to thank here one of the attendants in the meeting, that is Ferran Radea, that I can see you here. So thanks to you because you were the first one who trust with our idea, and then 20 years after we have the reality. So how we do that? So we started, of course, at lab scale in the laboratory. We moved to pilot plan, and then we went to full plan. In 2000 was when we started with the partial nitrification study and the anamox biomass. I must say that 20 years ago, there was not so much anamox biomass in the world. So we were obliged to enrich our own anamox biomass from nothing. So we used some inoculums from different places. And finally, in 2007, we get it. We get the anamox biomass, but under synthetic conditions. Of course, we evolved afterwards during the next years just to testing the anamox technology at different leachate conditions, different kinds of leachates. I mean, young and old or mature leachates from different sites and everything else. But then in 2011, we moved to the scale-up. That means to the construction of a full plan. We select the selection of the Corsa landfill site, but of course, the selection is not straightforward, so we need to make some kind of test in the pilot plan, creating real leachate in each case. We need to design the full plan, and finally the construction. So in 2014, we start the operation of the plan, and after 2 years, we can say that we get it. So it was working. It was really, really fine. So it was in 2016. But I would like to also to explain the last 4 years of operation of the plan. So it's not always easy, it seems, because the leachate is changing over time. So during the last years, the landfill site was closed, but we still have leachate, and the leachate was changing a lot. So we have some troubles, and I will focus my presentation basically in the last 4 years of the plan, in the full plan. So just to take an idea of how it's changing the leachate. So just remember, in the first stage when we started the plan, these are the main conditions of the leachate. So we are talking about a conductivity of 26 millisiemens per centimeter, and ammonia contents of about 2 grams per liter. So it was more or less the initial composition. But when we move over time, what we observed is that we have changed a lot the composition of our leachate. So we have practically doubled the conductivity of the leachate. We have increased a lot also the nitrogen contents, or the ammonia contents of the leachate, but also changes in the COD, not so heavy, but in the COD, but also an increase of the alkalinity. This is basically due to the matured leachate that we have obtained during this time, because no more waste was entering at the landfill, right? So, which is the experience? You can see here, for example, the evolution from 2017 up to today. This is the last data is from March this year. So we can see here, first of all, the evolution of ammonia. That is this point here. The evolution of ammonia at the leachate, sorry. this was the effluent from the partial nitrification reactor, only for the ammonia. And this is the composition of the ammonia at the effluent of the anammox reactor. So remember that we have in a two-stage. So we have leachate, effluent from partial nitrification, effluent from the anammox. With this data, it seems that it's working fine, but it's not working all fine, of course, because in spite that we have deal with increases of nitrogen contents in the leachate, if we look at the nitrogen removal rate, this was the stable operation, but suddenly in a period we observed a change in the activity. So we lost the activity, and we didn't know why. So for that, it was early last starting. It was in January last year, more or less, that we observed this kind of problem. So we need to try to solve it and to look for the problems and to see if we are able to adapt to this new kind of leachate. So what we expected was that we had some kind of inhibition of the biomass because of the high conductivity that we observed. So we expected that, first of all, are we able to acclimate the biomass to this high conductivity? We see that it was not possible, and then we try to move to a process control recovery by applying some kind of dilution that we will explain afterwards, right? If we look at the partial nitrification reactor, so the first reactor that we have in our Panamox process, we can see, for example, the evolution of the alkalinity. This is the alkalinity of the leachate, it's the green line. The yellow one is alkalinity at the entrance of the partial nitrification reactor. So we need to control the alkalinity that we are feeding in the SBR reactor.
1 minute, Jesus.
1 minute? Come on. So I will go rapid. I will go fast, sorry. So as you can see, we can control the ratio of the influent, and then at the effluent we obtain close to a stoichiometric value of the nitrite to ammonium ratio. Right. So there is, at the end, we have no problems with the partial nitrification reactor, but in the anammox we try to solve this kind of loss of activity, and our idea was basically to try to understand what was happening. Right. Just a minute. Okay, so we study in the phase one. What we first do was just to study the process, to analyze exactly what was happening. We tried to recover the biomass by adaptation. It was not possible. And then at the last phase, the phase 3, what we performed was a suitable control of the conductivity to try to recover the technology. So what we obtained, as you can see here, is that at the end, we were able to recover the efficiency up to 95% of nitrogen removal in the global process with a high activity in the reactor, right? So this is how the conductivity was evolving during the last year in 2019. And we can see also two kinds of process that we applied to perform the dilution. First of all, to make a dilution in the PN reactor, but then we moved directly to the anammox reactor. It was basically to optimize the operational conditions, right? So this is a general overview of the process, and then at the end of this recovery process, up today, we are in a conductivity control around 25 millisiemens per centimeter, with a nitrogen loading rate increased up to 1 kilo per cubic meter per day, right? So this is an example of the anammox biomass that we have early this year with a classical reddish color. And what you can see is that now the better is before than in 2019. So concluding, sorry. What we can see is that Panamox in our case is a Metronat technology. In our case, it's a two-stage process that can easily adapt to the leachate characteristics. The partial nitrification is mainly focused to biodegradable organic matter reduction and achievement of a suitable anammox influent. The anammox reactor works even at extreme conditions, but of course you need to know, and you need a lot of knowledge in order to implement this. Our control strategy is really, really easy. First of all, the partial nitrification is just controlling the alkalinity to total nitrogen influent ratio. And the NMOX, if you are feeding with a correct ratio between nitrite and ammonia, there is no problem to operate. But in our case, we introduce a dilution just to deal with the inhibition issues. So, and if we look at the economics of the process, during the first years of operation, we can say that we have a reduction of up to 40% of the leachate treatment costs. So thank you very much for your attention, and of course I will be proud to show you. I'm sorry, but with everything. But if I had time, I would like to show you a screenshot, online or live screenshot of the Panamox process. Can I for 20 seconds?
Let's do it, Jesus.
Thank you very much, Jose Ramon. So I will change now from the application. It's only 20 seconds, sorry. And okay, is this one? So this is the screenshot that is nowadays working in the in the Panamox process at Corsa landfill site. And we can see here, for example, the figures of the partial nitrification reactor. You can see here the time that is nowadays. So it's you can see here the date. And this is the evolution of the classical cycles with the pH decreasing and everything else. And also I would like to show the Panamox reactor that, for example, this is the starting of a cycle. And we can see the increase of the pH that is then reduced because of the addition of acid just to control the pH between a range. And this is the evolution. And that's all. Of course, all the parameters and so on, they are included in order to operate properly. So thank you very much for your attention. And thank you, Jose Ramon, for
the very nice presentation
and
the strong background you have in the process, and happy to, of course, we shared our experience in Panamox for already many years, so happy to see how successful you went in this case. Okay, so since we are running out of time, let's go faster. And now we move to Francisco Corona from the Fundación Cartif that will talk about the LIFE Leaches project. Please, Francisco,
Hello.
the floor is yours.
Thank you. I think to share my presentation. Could you see the presentation? It's okay?
Perfectly. Yeah, it works.
Hello to everyone. Thank you very much for the invitation and for the introduction. My name is Francisco Corona. I belong to Fundación Cartif, an RTD located in Valladolid, Spain. And today I'm going to talk about LIFE Leaches project. Firstly, we take a look to the waste situation. In Europe, every year, 16 tons of material are used by person, and of these tons, 6 are converted into waste. Solid waste can be disposed in various ways. Incineration, landfilling, recycling, and composting. And landfilling has the most commonly used solid waste disposal, especially in Spain or other Mediterranean countries. On the other hand, the main problem of these landfills is the greenhouse gases and the leachate that generates. In this picture, we can see the evolution of waste treatment technologies, and in this, we can see that in the last years, recycling and composting, are more popular than other options than landfilling. The leachate is a liquid fraction of the already existing moisture of liquid within the solid waste. Landfills generate leachate until 50 years after the closure. More or less 10 cubic meters of leachate is produced per 150 tons of solid waste. And one of the big problems where we can see in the previous presentation is that the leachate composition is not very homogeneous. So this composition depends on several factors such as the waste characteristics, the moisture content, the climatic conditions, the degree of the compactation, and for sure the age of the landfill. The problem is one or unique treatment option cannot be suggested because the composition is not homogeneous. Leachate, the problem is we have the leachate has hazardous constituents and potential ecotoxicological effects. The main components of the leachate are the organic matter, the dissolved organic matter, the inorganic components, the heavy metals, and the xenobiotic compounds. This is this table. In this table, we can see the difference of the general composition of the leachate respect of the age of the leachate. The characteristics depend on the age because we can see that the younger leachate have a high amount of organic matter and a lower value of pH. When the leachate cannot treat, we can recycle it to the composting solid waste, or we can set this waste, this liquid waste, to the wastewater treatment plant. Taking into account these considerations and these environmental problems, the objective of the LIFE project is to demonstrate the feasibility of an innovative in-situ treatment process to treat the leachate generated in landfills and wastewater treatment plants. This project proposes sustainable management composed by a solar panels technology to evaporate the leachate, and the vapor is condensed to follow a step of forward osmosis. Because forward osmosis requires less energy than reverse osmosis and has more fouling problems. The project is easy to replicate and easy to operate and maintain. And this solution is an universal solution independent of the leachate composition. This is the general figures of the project. We are three beneficiaries, three partners, two from Spain. Cardiff is the leader or the coordinator, and Triton is the technical partner. Another RT partner is the University of Athens. These days we are managing and project extension because we are delaying these activities mainly due to the COVID breakdown. This is a general diagram of the process. We can see that the leachate is treated by solar technology, and the forward osmosis is used in the second step to treat the liquid fraction condensed by the solar evaporation in the first step. The liquid obtained after the forward osmosis the composition is according to the legislation to use cleaning or other use of water. And the semi-solid fraction obtained in the first and in the second step, we use or is valorized to use at formulate ceramic products. It's an ingredient to the ceramic products. This is the general picture of the prototype. The proposed treatment system is composed two main separation process: the solar panels to evaporate and condensate the leachate in the first step, and the forward osmosis in the second step. The system we place in 3 containers, and is the typical dimensions of marine containers, and and the prototype will be operate in 2 demonstration sites: waste treatment center in Spain, in Lanzarote, and a landfill in Athens, in Greece. And the maximum capacity of the plant is between 8 or 9 cubic meters per day. This is a first diagram of the project. It's the typical distribution of a LIFE project with the preparatory actions, implementation action, monitoring, dissemination, and management actions. Prior to the construction of the demonstration plant, we carry out a lab scale test with the solar evaporation condensation and with the forward osmosis prototype. The aim of this test is to optimize the operating condition of each of the 2 technologies, and the results we serve at basis of the design of the demonstration plant. One important point is that the limits of the effluent quality that we have or we use are the more restrictive limits for the Spanish and Greek legislation, because the effluent will be used in the demonstration sites in Spain and in Greece. In the first of all, we carry out the characterization of the leachate from the wastewater treatment plant and the landfill. And after all, we carry out experimental test with the evaporation condensation technology at lab scale. We study different levels of amount of leachate to be treated, the operation time, the amount of solar radiation, and other important elements. And this is the solar module used at lab scale. After, we use the leachate obtained from the evaporation condensation process, and this liquid fraction was used as raw material to the forward osmosis. This is a picture of the small forward osmosis used at lab scale, and we use different experimental conditions to optimize the process parameters, the membrane quality, and for sure to define the membrane area required for the demonstration plan. And finally,
1 minute left, Francisco.
We obtain the. I go fast. This is a general process diagram of the process to define the demonstration plan. This is the photograph of the demonstration plan that has been commissioned during the last month. And this is the final result, the result obtained so far. And these results are very promising because we have to reduce the main parameters of the effluent below to the limits set by the legislation. All the results or parameter consultation have been considered reduced. The COD reduced of 99%. A very low metal concentration, and the reduction of sodium concentration of 98%. And for sure, the sludge obtained in there is optimal for the ceramic valorization. As conclusions, the optimization of operating and process conditions for solar evaporation technology forward osmosis were carried out. We select the aquaporin hollow fiber membrane as forward osmosis for the forward osmosis process. We recover up to 70–60% of the leachate, and the quality of the final effluent is according to the legislation, and the sludge obtained is optimal to use ceramic to the formulation of the ceramic components. Thank you very much for your attention. Please follow us in our social networks to know more about the project, and that's all. Thank you.
Thank you very much, Francisco. Very interesting approach. So let's move now to the final talk, and I'm very happy and honored to introduce you one of the popes, I would say, of anaerobic digestion in Spain and in the world. Xavier Flotats will talk about its experience and how we can harvests from wastewater treatment to wastewater processing. So we need to get rid of the waste world, and let's see how Xavier tackles this issue. Welcome, Xavier, and we are very honored to have you as the closing speaker for this virtual event.
Thank you very much, Jose, and good afternoon, everybody. During my speech, I will not show experimental results or propose a new technology, but provide some reflections about the need to modify our vision and our nomenclature related to this big role of the waste and the wastewater treatment. Our old economic model was based on the concept of an open system for energy and materials with the illusion or a hope of a continuous motion machine. We know today that this is impossible. Thermodynamics limits this model, and we must move to the circular economy model. A closed system for materials and open system for energy, where materials can be produced, transformed, and used based on renewable materials and renewable energy. At this moment, we are in transition to the circular economy, following a path plenty of conflicts and uncertainties, because our rules and our habits belong to the old economic model. So, but this transition is also plenty of opportunities. We must realize that all the energy content of our organic matter we found in waste stream. For example, here is a scheme of the food chain. All the materials we found as effluents, residual effluents, liquid, solid, and gases, all the organic, all the energy of these organic compounds are coming from photosynthesis, from the energy captured from solar energy. To remove this organic matter using aerobic processes dissipates this energy, and also is necessary to expend energy for transferring the oxygen. To use anaerobic systems, that energy captured by photosynthesis can be mainly recovered in the form of methane, a renewable gas. So it is possible to recover part of this energy, but we must realize also that all the nutrients we found, all the flow, the mass flow of the nutrients we found in the effluents and the residual effluents are the same or almost the same, the mass flow of the nutrients feeding all this system. So my point is that it's necessary to recover these nutrients in order to feed again this machine. Is it important to recover nutrients? Well, of course. Ammonia and nitrogen fertilizers, that is the ammonia and the nitrogen we found in the effluents, are produced mainly by the Haber-Bosch process, where hydrogen is coming from reforming natural gas. We can produce this hydrogen by solar energy, but the priority should be to recover this ammonia as much as possible. Phosphorus, the reserves of phosphorus are limited and mainly located in a few places, mainly in Western Sahara, the old Spanish colonies. And probably if we don't minimize the consumption of phosphorus and we recover all the lost phosphorus, in the future we will have a geopolitical strategic problem. Nitrogen, ammonia, and phosphorus can be recovered following different processes and using different technologies, and we can see in these pictures of crystals of ammonium sulfate and struvite, produce it after digested because anaerobic digestion necessity for the mineralization. If we see the hierarchy, the old hierarchy of valorization of waste, it is actually to enlarge for taking into account new processes and new systems, beginning with landfilling that we know that we must always avoid, anaerobic digestion, composting, pyrolysis, gasification, dark fermentation, biopolymer synthesis, and also recirculating in the system some residues of these processes to produce new goods, and realize that all these processes can produce new materials, new energy vectors as char, as carboxylic acid, lactic acid, hydrogen, methane, compost, etc. Some processes are, the technology readiness level is low, but we know we must develop these technologies because for the produced products, the profit could be very high. Well, if we realize these products, the market price of these products, as acetic acid, ethanol, or butyric acid, or lactic acid, or polylactic, the market price of these products are higher than methane or digestate of compost. So we have the opportunity to produce these materials. We need to produce materials because if we want to go to a circular economy. An example of how it's possible to do something, we can have a deep view in the anaerobic digestion process and the reactions, and what could be possible combining two anaerobic digestion systems. In the first one could be operated or controlled to optimize the production and the recovery of an intermediate as volatile fatty acid, butyric acid, or propionic, or caproic, or acetic acid, etc. In the second reactor, or interface, or in the effluent, it is possible to recover ammonia using hydrophobic membranes, stripping, distillation, etc. In the second reactor, we recover methane, but in the first, it is possible to recover some hydrogen. What are we doing if we follow this scheme? We are treating a waste, or we are processing a resource. My point is that we do, and actually we want to do, or we need to do more than just treat a waste. Anaerobic digestion is a very well-known technology, but I want to show that we have technologies based on anaerobic digestion process adapted at almost any feeding, covering a peak slurry lagoon for recovering gas, VSTR, path flow reactors for high solid content wastes, the membrane anaerobic bioreactor, reactors based on biofilms, the ESV, and the further developments enhancing the contact. We realize that we have technologies adapted to from low to high organic loading rate, from low to high solid contents, etc. So the question is why we don't use more these options anywhere. And my answer is that probably the market is not paying for all the benefits this process provides. Realize that always we mitigate greenhouse emissions. Preliminary, three questions for thinking. What to do? To treat a waste or to process the resource? The microchip for me is important because this defines the objective and the view of our business. A treatment plant is a treatment plant just or is a factory? In the first case, we modify the characteristics just for fitting the legal environmental requirements. If we think that we have a factory, we fit the legal requirements, of course, but we produce new goods and new services and new energy vectors and new materials. Who are our customers? In the first case, the customers are the local or regional authorities, usually, or an industry who buy our services for solving its environmental problem. If we have a factory, our customers are the authorities, of course, because we are producing new water, for example, but also the companies who will use or will buy our goods and services, pharmacies, industrial manufacturers, energy suppliers, etc. What are our objectives or expectations? Well, in the first case, my objective will be to trade more waste or more wastewater, because the more waste I trade, the more money I will have. No? If I have a factory, my objective will be to produce quality products. The higher the quality of the products, the higher the revenue per unit of products. For example, in a composting plant, who is the customer? If the customer is the local authority, the more waste I will trade, the more money I will gain. But if the customer is the farmer, my objective will be to produce a good compost. This is not the same. My point is that customers define the demand and the business kind. The conclusion is in the context of a circular economy to which we are in transition, in a difficult transition, it is necessary to modify vision, objectives, and nomenclature. Waste, solid waste, wastewater, gas waste, all are resources. And these resources must be processed to produce, not just to trade to fit environmental regulations. To process to produce valuable quality products. We have technology and we need to develop more technology. It is not easy, for example, to recover ammonia. A low concentration ammonia, the solution is an amox, but at higher concentration, we must try to recover. The market is complex. In this market, there are a lot of possible customers, a lot of persons with different languages, different interests. This is complex, but it's clear that the market of the quality products produced from wastes and wastewater is a market that must be strengthened. Is a market that must be regulated, as is doing the European Union with all the legislative package around the circular economy. Finally, I like to pose a question. Is it possible in the future that what we know that a waste treatment plant or a wastewater treatment plant will be an strategic industrial producer of raw materials, energy, goods, and services, and then to be under the umbrella of a Ministry of Industry? Thank you very much for your attention.
Thank you very much, Javier. I think you did an amazing presentation, and it couldn't be a better speaker for closing this virtual event. I hope that all the attendees have still the energy to stay here until the end, and I pretty much appreciate your last sentence. No, I think it's a different view, and I think the future is there, and we need to move towards this direction. So hopefully, this kind of projects where we involve public and private entities and with European funding that gives us the chance to disseminate what we are doing, I think it's important tool to arise these points and to make the society aware of the challenges we are facing. But I'm sorry for the small delay we have, but let's take some questions from the audience, and I will try to close as soon as possible so we don't steal you too much time. So I've seen that Tony has a question, and please, to the audience, feel free to raise your hands, and you probably have a lot of questions to these 4 wonderful speakers of the wastewater panel. And please, Tony, start with your question.
Thank you, Jose. My question is addressed to Professor Kolprim. It's about the experience that you had with Anamox treating the leachate, which is very similar to the experience that we had, as you know, in Metamorphosis, and that's why I'm really interested. Especially, I want to know, I think you speak or you mention things about the conductivity, the electrical conductivity, but I think I miss probably the importance of this parameter and about the dilution of the inlet wastewater. Can you please try to summarize what is the weight or the implications of the high conductivity this wastewater in your experience? Thank you.
Okay, thank you, Antonio. The issue that we observed during the last year was, first of all, the change of the leachate, right? So we lose the activity, and we didn't know why we lose the activity of the Anamox reactor. So our idea was, first of all, to try to analyze everything else in the plan. And what we observed was an important increase of the conductivity on the leachate up to 50 millisiemens per centimeter, right? So we have read something about high conductivity and Anamox, and there are some authors that they say that it's possible to recover the activity just by waiting a lot of time for a biomass acclimatization, right? So because it was before the summertime and everything else, we decided to test the biomass acclimatization for 2-3 months, more or less. But what we observed was that the activity was recovering, but was really, really slowly, and it was not possible to recover the activity. So at the end, what we decided was to come back to the conductivity that the biomass was used to work. So we induce a dilution by rainwater from the landfill itself. So you know that in the landfill you need to recover your rainwater that is surrounding all the landfill. So it's a clean water, more or less, with a low content of organic matter and salts. And we perform this dilution with this point, right? So then once we reduce the conductivity from 50 millisiemens to 25, we recover rapidly the activity of the Anamox. And what we have observed is that nowadays it's working fine. So, but this is the facts, right? But the problem if the conductivity is a problem or not in the Anamox, I'm not sure about that, because what we have also is that the organic matter changed in the leachate. So probably we have some refractory compounds in the leachate that can also inhibit the biomass. So what we don't know now is that if this dilution if the dilution reduces the conductivity and then it's working fine, or the dilution reduces the concentration of some inhibitory compounds and then we recover the activity. So we don't know the case, so which was the cause of the Anamox activity loss, but what was a reality was that when controlling the conductivity to 25 with the dilution process, it was okay, we're working fine. At the end, before using the rainwater collected in the landfill, we also were testing with permeate from a reverse osmosis of the effluent of the Anamox. So it was also an option. I mean, if you don't have this dilution with rainwater, at the effluent of the Anamox, you can introduce a reverse osmosis unit So you will have a concentrate with all the salts. The advantage is that you will get also an effluent with a lower conductivity. And then you can also recycle part of this water, this recovered water, because we are talking about 1 millisiemens permeate from the reverse osmosis. We checked that and it also was working, right? But of course, the cost of using rainwater of permeate from reverse osmosis is not the same. So it's better to use with that, right? And at the end, you need to treat this rainwater because you cannot dispose directly to the environment, you know, because it's collected inside of the landfill, right? I don't know, Antonio.
Thank you. Thank you. Thank you very much. We have another question by Carlos Ramos from Eurecat again. Hello, Carlos. Please ask your question.
Thank you. I think the presentation reflects the real situation here and how the ANAMOX is going to be implemented. And I have two questions. One question, this is for Maria and also for Jesus. You are treating the most extreme cases to implement the ANAMOX to the real world. Maria is working with very low concentration of ammonium, so the inhibition and the control is very complex and it's more difficult. And Jesus is working with the high extreme concentration of the ammonium, which is you are going to have more inhibitions and more problems to run the process. So in the future, how do you see the implementation of the ANAMOX into more wastewater treatment plants or new kinds of wastewater like you are treating right now?
So if you don't mind, I start. From our point of view, from the point of view of Acciona, ANAMOX is a suitable technology for mainstream because it has many advantages. And we are focusing on new strategies to overcome barriers caused by the lower strength of the wastewater we are treating. We are working with free nitrous acid, free ammonia, oxygen control, and other strategies that are adapted from high concentrated streams and adapted to the low concentrated streams as the ones we are treating with. So we are with this line. We are investing efforts in developing these new strategies because we are confident that we can export that technology to the mainstream also.
Well, in my case, for high strength wastewaters, as the case of the leachate, of even the digestate from anaerobic digester, for example, I think the ANAMOX it's a material technology, so it can be easily applied, right? But also we must also take into account which is the final objective of our wastewater treatment. So, for example, you have seen that in our case we are an effluent lower than 200 milligrams per liter of nitrogen. It's really a high content of nitrogen, for example, compared to Maria del Mar, right? Because it's really, really high. So, but it's because the landfill don't need to reach a lower value, right? But the big problem of the ANAMOX, it's always the same. So in the case of high contents of ammonia, it's the residual ammonia that you have, because you need to always to work with an excess of ammonia in order to avoid the limitation of nitrite, right? So we are always running at zero of nitrite, so you always need some nitrogen inside. If you are planning to go, for example, in mainstream, the low levels of nitrogen that you can have, we are talking about 50 milligrams per liter of nitrogen in a urban wastewater treatment plant. Here there is another problem also. It's that you have a low level of nitrogen, so you can have an effluent with some nitrate that we need also to be removed, because the effluent restriction of total nitrogen are really high. So this is also a big problem here to try to solve. But I'm sure that on the time we will be able to deal with that. So in mainstream wastewater treatment, of urban wastewater treatment. I don't know the experience of Maria del Mar, but I'm sure that can be done, but it's not easy. Also temperature, of course.
From our point of view, the main bottleneck is partial nitrification more than the anamox itself in mainstream. For us to control, what are we seeing? Is hard for us to obtain a stable nitration process, because it's easier for the mainstream to change all the ammonia to nitrate instead of nitrate. So our efforts are more devoted to that first step than to the anamox, because from what we see is that anamox can cope with that nitrate and that ammonia we can give them. So our main efforts are focused on obtaining unstable partial nitrification, try to reduce the amount of nitrate we generate, and try to stabilize the AOV against the NOV.
Thank you. I think we made a good understanding, and we went through a lot within this anamox world. I would just add to finish it that I believe anamox can deal with this high conductivity or high strength and low concentration of ammonium, because you all know that around 25 to 30% of the nitrogen we breathe is coming from anamox in the deep sea, where the ammonia concentration is very low and where the salinity is very high. So it's likely that the only barrier there is between this technology and its application in the real world is our knowledge. So it will come, and I'm happy to have you on board, and the more projects we have within this topic, the better it will go, and we will see probably in the near future many plants equipped with this technology. Just to close the event, I would like to ask Xavier, because I like very much your approach, your opinion or your advice on who should be leading this change. I mean, should it be the minister? So should it go from a very high political level? Because we have seen that Europe has delivered many drafts dealing with circular economy, how we should move our way to handle products and treat waste and bring new lives to the products. But my feeling, at least, is that in the real world, it's still not happening really seriously. So who should be driving the change? Should it be the society? Should it be the very top level political layers? Or should it be a change into our minds as a whole society? What's your opinion?
Well, first of all, it's very important to produce a change in our brains, to treat waste or to treat wastewater just for fitting the regulation is very comfortable. So it's very comfortable. If the market is not demanding new products, is not demanding butyric acid for producing some bioplastic, if there is not a demand, so it's very difficult. So somebody must push fast. And this is a responsibility of our authorities. For example, the certificate of origin of biomethane. This is obvious that is necessary. This is obvious that is necessary. Why in our country we have these certificates yet? Why? So the authorities must be the first to push. It must be the first to organize, to drive, to open opportunities, to explain, and to fix, some planning, some objectives, some milestones. Here in our country, we haven't milestones for a circular economy, milestones, or milestones for renewable energy, just for example, the renewable gases. And you can see that France is planning to cover all the demand of natural gas, decreasing the demand, of course, with renewable gases by into 30 years. Denmark into 15 years, etc. What is our objective? The first to must push, the first to must build the ways are the authorities, and then we need some change in our views and our brains, and to create companies demanding and producing these intermediate products, etc.
Perfect. Thank you, Xavier. So with this, I think we made it. And I just wanted to share with you a final slide. So, and we close the session. Let me see here. Okay. Because of course I cannot close the event without saying thanks to all of you first. To all the attendees, you had the patience to be here this whole morning and afternoon with us. Of course, it was a long trip from 2015 and even earlier when we started talking about this project. And of course, there are many people involved in all this way out and all these magnificent results we just presented. It was hard working team with excellent professionals. And of course, it wouldn't have been possible with EU funds. So thank you, European Union. Thank you, EASME, and the officer, Van Decker, that visited us. And thank you also to the monitoring team, Elena and Mariona, that gave us and directed our work very carefully throughout the whole life of the project. And thank to all the partners. It was amazing having you on board and coordinating such a dedicated team. And of course, thank you, AMB, for organizing this virtual event. It's not easy. It's always a challenge to make these virtual sessions. So please, I would like the audience to give an applause to, especially to Julia and Gloria and all the AMB team, the technical and the directors. Thank you very much. From my side, it's all. Please stay safe under this weird pandemic situation. I hope we can come back to the real events where we can meet, take some coffees and discuss further plans and so on. And I don't know, Gloria or Julia, or if someone from IMB want to say something else. For me, it was all, and thank you very much, and see you in the next events and next projects. Bye-bye.
Bye.
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 Bye. Thank you.
Thank you.
Bye. Thank you.
Thank you to everybody.
Thank you very much.
Thank you very much. See you. Bye.
Thank you. Bye.